¿Qué tal? Sí, sí, muy bien. ¿No? Lo que no tengo es acceso para compartir. No sé si eso lo ponen ustedes. Ah, vale, vale. Sí, creo que estaba Flavio por ahí. Ahora ya no lo veo. Sí, sí. Ah, vale, vale, vale.
Hola, Mara.
Hola, buen día. Ahora sí.
Hola, Valeria. Hola, vale.
¿Qué tal?
Vale, te voy a hacer moderadora, ¿vale? Y
Ah,
así,
vale, eso te estaba diciendo antes que no me escuchabas, que no podía ni compartir ni...
vale, ya eres moderadora. Entonces, puedes
Ah,
hacer presentadoras y hacer presentadora quien quiera. ¿Vale? Pues nada, cuando quieras puedes compartir tu pantalla y así ya se apaga el vídeo ese que tengo ahí puesto. Con la presentación que quieras. Vale. Y hoy no tenemos muchos teléfonos. Este vídeo también está interesante. Si no, lo hacemos para ponerlo. Sí.
bien. Ah, ok.
Puedes elegir la pantalla, o completa
Ahí.
o
Ah,
sería.
ok, ok, acá. Ya. ¿La ven? Sí, perfecto.
Es que aquí me pregunta la cuestión. ¿Cómo pasó a que parezca la tormenta? Ese no supo que están acercadas. Ahora sí. Vale, la vamos de arriba.
Mira que Gonzalo que te pide.
Bueno, voy a desconectar el vídeo de YouTube y conecto ya. Vale, a partir de ahora, Florencia, en cuanto en un minuto estaremos transmitiendo por YouTube también. ¿Vale?
Vale, para no hacer cosas raras.
Jalar el gato, eso.
¿Dejo la cámara prendida? Bueno, sí, mejor, ¿no?
Sí, mejor.
Vale. Vamos a subir plano mejor.
Ya está mirando en Google. El café está en la nevera. La botella de andar fría, o sea, que vuelvo a calentar. Vale. Luego está algún tipo que trabaja aquí. Porque se quedará ahí ya. Lo haremos. Hay una canción. Vale. 1 minute to go. Already. Debemos por ahí. ¿Cómo preferís? ¿Que presente por eso?
No lo grabamos por acá entonces, ¿no? Al final, sí.
¿Cómo?
Que no grabamos por acá tampoco, si ya queda en el YouTube.
Dale a grabar. Bueno, espera, le doy yo. Yo no le di ayer porque al final YouTube lo hace también. ¿No? Sí, pero es por tener otra seguridad, ¿no? Si se nos olvida, no hay problema. It's 9:59. 30 seconds. Okay, I think it's time to start. We don't have many people online, but we have a lot of people here physically. Life is coming back again. So it's a pleasure for me to introduce our first speaker of today's session. Florencia Tepa Pañas is a postdoc here in our group, and we are doing interesting things on different topics, mainly in cosmology and astrophysics. And today she's going to speak about her work in collaboration with José Beltrán and other colleagues. I don't see, okay. I can see all the other names, but anyway, and the title of the talk is one, probing elastic interactions in the dark sector. So, Valencia, you can start whenever you want.
Okay, thanks. Good morning, everybody. Thanks for being there and a nice presentation. So today I'm going to present this work, which is already recently published, in collaboration with José Beltrán, Dario Bettoni, David Figueruelo, and Shinji Tsujikawa. And the idea of the work is to study some cosmological models with elastic interactions in the dark sector, with the aim of reducing the clustering. So these are the motivations for this work, why we want to reduce the clustering. Well, we are in the era of precision for cosmology. We have access to a lot of data coming from different observables, such as supernovae, galaxy surveys, cluster counts, weak lensing, and of course, the anisotropies of a cosmic microwave background. We have a very good model, lambda cold dark matter model, able to explain, to put all together these observations and to describe very well the evolution of the universe. Nevertheless, there are some tensions among the value of some of the parameters that this model has, some free parameters, in particular, the H0 tension, which arises when we put constraints on this parameter using data from different epochs of the universe. For example, we obtain a value nearly 67 when we use early data from Planck, for example, and higher values, larger value, sorry, when we use late data coming from supernovae. Well, there is, this is not the only tension the model presents. I mean, we can find in the parameters of the model, but also the growth tension, which is now the growth tension involving this parameter S8 or sigma 8, which is associated with the clustering, the growth of structure. And we see that when we put constraints on this parameter using Planck data, we obtain values that are larger than the values preferred for low redshift observations, weak lensing or cluster counts. So we want to construct or to study models able to alleviate this tension, this particular tension in the growth parameter, and obtain values more compatible with low redshift data. So to do that, we will add to the our paella of the universe a new ingredient that is the interaction between the dark sector, that is models of dark energy or dark matter able to naturally alleviate these tensions. Why? Well, basically because if we put interactions with dark matter with another fluid, pressureful fluid, the clustering will be reduced, will be more efficient, less efficient, sorry. And not only that, but we want to do that in a way that only the perturbations are sensitive to the interaction, while the background evolution is oblivious to it. Why? Well, because as I already said, the background works very well, the evolution of the background in the lambda cold dark matter model. And on the other hand, if we take this approach, we are able to distinguish the effects of the perturbations from the effects of the evolution of the background. So with this in mind, we want to construct to add these interactions in a fully covariant way, and we are taking two approaches. We can add an interaction in the dark sector at the level of the equation of motions for the dark matter and dark energy. And this interaction is proportional to the relative velocity of both fluids, in a way that the whole energy momentum tensor will be conserved. So only the modifications only appear in the Euler equation. And this alpha is the coupling parameter that for the strength of the interaction. The other approach is going through the Lagrangian formalism, proposing this action, an action of this form, where we have the usual term for gravity. This second term describes the fluids in a Schutz-Sorkin formalism. And the last term describes the dark sector interactions that basically depend on this arbitrary function f of z, where z is defined in this way. At the background takes a constant value -1. And this kind of interactions, again, will be proportional to the relative velocity of the fluids, and also to the relative acceleration of both fluids. And well, okay, we are considering the standard cold dark matter fluid, and for the dark energy, we will consider a fluid that behaves as a dark radiation at early times, and then as a pure cosmological model, constant, sorry, at late times. So let's see how is the form of the evolution equations for the scalar perturbations. In the case of the first model, this is the set of coupling equations. Here are the terms involving the interaction between dark matter and dark energy. We can see here that the terms are proportional to the relative velocity, and this gamma and R are the rate of the interaction. We are using a dimensionless parameter alpha, and hereafter what we called alpha cold dark matter is LW cold dark matter. That is the standard cold dark matter fluid, and a dynamical dark energy with a constant equation of state W, plus the interaction. And also we will let free the parameter N effective, which is associated to the relativistic species at early times. in order to explore also if these kind of models can alleviate the H0 tension. So this model has 3 extra parameters respect to the lambda cold dark matter: W, alpha, and N effective. The second model, BCDM, arises this set of coupling equations for the dark sector. Here we have the terms associated to the interaction. We can see here that they depend on the relative velocity and also on the relative acceleration, as I already said. And the interaction, when we solve these equations for the velocity and the density perturbations for both fluids, we can put the interaction in terms of this constant, the strength of the interactions and the interaction in terms of this constant B, which is nothing but the first derivative of this constant function f, evaluated at the background. So for any form of the function f, at the end, the interaction will be parameterized by this constant B, which is taken also dimensionless. So hereafter, what we call B cold dark matter is the standard lambda cold dark matter plus an additional dark radiation. As I say, the dark fluid is described by dark radiation at early times and then a pure cosmological constant at late times, plus the interaction. So we have here 2 extra parameters with respect to the lambda cold dark matter model. So, okay, what are the effects on the observation of the cosmological observables? Well, let's start seeing what happened with the CMB. We can see here that the effects on the CMB are not too big. This is what we expect, indeed, because we are not modifying the background, so the effects are not so big. We can see here that if we increase the value of the parameter, the strength of the interaction, we see some differences in the height of the first peak, but this is because not for the interaction, but for the additional amount of dark radiation that we are adding in this model, and in this case, because of the different value of the relativistic species. So in the CMB, there are not appreciable effects in these models. Nevertheless, we have considerable effects on the matter power spectrum, as is desirable. We can see that when we increase the strength of the interaction, this is for the case of alpha cold dark matter, we see a suppression. There is a suppression on the matter power spectrum at small scales. Okay, and we can see also that not only a suppression, but also there is a shift in the redshift at which that suppression starts. The shift to bigger scales, larger scales. Sorry. Okay, in this case, for the alpha cold dark matter model, the amount of extra radiation doesn't have a relevant role on the matter power spectrum. The effect is dominated by the strength of the interaction. In the case of B cold dark matter model, we can observe also a pronounced suppression at small scales on the matter power spectrum when we increase the parameter. the strength of the interaction, the parameter B. And we see here that when we change the amount of dark radiation, the additional dark radiation, in this case, it has an important role. It the scale at which the suppression starts will be shifted more or less depend on the amount of radiation. And this is what we expect, because this radiation is the fluid which is interacting with dark matter. So we expect that that interaction directly affects the matter power spectrum. Okay, so our models are going through the direction we wanted, that is reduce the clustering. So let's see now what happened when we try to put constraints on these parameters using cosmological data. By the way, these numerical computations were done using a modified version of the CAM code for the evolution of the cosmological perturbations. So when we constrain the parameters using cosmological data sets, we obtain the following results. First of all, the data set, the standard data set that we are using here are the Planck temperature polarization and lensing for the CMB, the combined data for BAO, and the last compilation for the supernovae pantheon. And what we obtain is that this is the plane sigma 8 against matter density. And we see here in light gray the values preferred for the lambda cold dark matter model, in blue for B cold dark matter, and in green for alpha cold dark matter model. And we see that the contours allow lower values of sigma 8. That means that we are going to this direction, which was the first motivation of study this kind of models. And when we add an additional constraint for the value of S8 obtained from Znaev-Seldovich cluster counts, which is represented by this gray band here, the fit is even better. This other plane is H0 against S8, and we see again that for both models, the values of S8 are lower. Nevertheless, we don't have an improvement in the for the value of H0. So these are other observational constraints. This in the top panel, sorry, we are showing sigma 8 versus the matter density, and we see that in both cases, in B cold dark matter model and alpha cold dark matter model, this color bar represents the strength of interaction, log B and log alpha, and we can see that for the strongest is the interaction, the lower values of sigma A we obtain. And in the lower panels, we can see the relation between H0 and sigma 8. We have here H0 versus N effective, or in this model, dark radiation. And we see that for the lambda cold dark matter model, in this case, the color bar is represented the values of sigma 8. There is a strong correlation between the values of sigma 8 and H0. So if we want to change one of them, the other will be affected. Nevertheless, for our models, it doesn't happen. I mean, we have here that we can see here that the correlation is not more present. So this is a good feature of this model, because we are able to alleviate the tension on the sigma 8 parameter without worsen the H0 value. So, well, these are the full constraint for all the parameters of the models. These panels were already shown. What I want to remark here are these panels in particular, which are showing the value of the parameter alpha and B. And the important feature here is that when we include the Sunayev-Seldovich data in our fittings, we are able to detect a non-vanishing value for the coupling parameter in both cases, in this case and in this case too, and B. So these are the final remarks of our work. We have studied observational constraints on a class of models featuring a dark sector with interactions, and the presence of a coupling of dark matter with a pressureful fluid reduces the growth of the growth of structures at late time, reduces the clustering. And the important one of the important remarks here is that these models seem to prefer only one tension at the time, but it's however interesting that improving one tension does not worsen the other, because the correlation in the plane S8 and against H0 is substantially reduced. So, well, it is this is the work I wanted to show you. Thanks for your attention. And if you have questions, I'll leave you the final remarks here to you. This is the full reference for the work if you want to see the details.
Very good. Thank you, Valencia, for your talk. Are there questions? Here first, here in the audience. Any comment? Oh, yes, please.
I think it may be a very nice question, but I saw you start from the so-called Schultz sorting action. You included some calculations within a fixed background in order, if I understood correctly. Can you hear me, by the way?
Sorry, what? Could you repeat the question? I cannot hear you.
Can speak, you know,
Okay.
Hi.
Yes.
Hi. I think it just a question. So I saw you started from the Schultz sorting action, which is,
yes.
If I understood correctly, you were fixing the background and then you were adding to it the perturbation. So my question is, then when you obtain the equations of motion, you also vary with respect to these perturbations. What is the effect of including these perturbations into the action? What effect it has on the equations of motion? What things do you get? It's just a very general question.
So on the background.
Sí, yes.
No, okay. Okay. We have not effects on the background. I mean, only the perturbations are modified. The evolution of the perturbation is modified. We fix this value without loss of generality. We fix, here. This Z, we can fix it at the background equal to -1 without loss of generality, and we don't change the background at all. I mean, only the perturbations at first order will fill the interaction. And the important feature is that the interaction is hidden by this constant value. I mean, we at first order, what is okay, the interaction depends on the first derivative of this function f evaluated at the background, independent of the form, the particular form of the function f.
Okay.
I don't know if I answered your question. Maybe Jose can.
So, Florencia, and this is not an approximation, right, for the background?
No.
This is so the background is unaffected, and
yes.
then you only,
yes. The background is unaffected, and the interactions only enter in the set of equations for the scalar perturbations. I mean, but it's not an approximation. We only take the first order in the scalar perturbations. We only take the first order.
Okay.
I don't know. Maybe Jose, you want to? Okay.
Any other question here in the audience? Comment? No. Nothing on the chat. I don't know YouTube if there's anyone.
I'm not seeing anything. I mean, there are no questions.
So I have a question regarding this slide number 7.
Regarding, sorry?
The slide number 7 here in your list.
Yes.
7 or 6? 6.
Okay, here.
8. Number 8. Sorry.
Okay.
Yeah, this is one relation. So lambda CDM is the upper envelope, right?
Yes, the lambda CDM is here. Is the black solid line here. So we have basically.
Okay. So we are on the same point. So I'm curious about this type of oscillations. So even if the magnitude is not as big as shown here, even if this model were not correct, but if we had some kind of oscillations like those, so would they be observationally accessible? I mean, I don't know if we have observational data for all the points on this curve. I would like to understand if at some point it would be possible to observe oscillation of that kind if they existed.
These observations, are you talking about?
From observations, yes.
These oscillations, sorry. Okay, these oscillations are indeed present here. Mm-hmm. And this is, I mean, these values for the B parameter are super exaggerated. I mean, we test some values in order to see how is the effect we expect, but then when we put this, when we fit this with real cosmological data, the value of B is it's super small. I mean, let me see here. I mean, we don't have this. This is just a value to understand what's happening with the model. But when we go here, we can see that here the value of B, this is the logarithm, it's really small. So at the end, the power spectrum will be will look very similar to the lambda Coulter matter. With the same little oscillations here, we observe also in the standard model. I don't know if
yes.
That's clear. Okay.
Yeah. Okay, so if there are no other questions or comments, I think we can thank Florencia again.
Thanks.
Now we can get ready for our next speaker. Aquí, ¿es la presentación está aquí?
Sí, tenemos la presentación. El dogma de contrato, pero el PowerPoint, porque el PDF no se comunica bien.
Vale, pues tendrás que pasarla a Samara. Bueno, creo que siempre hay un problema, ¿no? Con el PowerPoint.
Vamos a intentar compartir la pantalla completa.
Es que creo que no pasa. No,
hay que compartir toda la pantalla, ¿no?
Toda la pantalla.
Vale.
Y si se guarda en PDF,
Es que no se ve nada.
Es que no, hay cosas que no se...
Próximos presentadores y me reunimos toda la pantalla, ¿no?
A ver si así funciona.
Y nos vamos a de forma pequeña. ¿Es esto todo lo grande que te puedo hacer?
No, dale a la pantalla completa.
No. Aquí.
Voy después de nada y veo mucho maldito.
Yo
¿Lo tienes? Y yo tengo la iniciativa. Tomando nota. Me ha apuntado uno para ayudar. Vale. Tienes ese. Perfecto. Okay, so it's a pleasure for me to introduce Pepe Maldonado, Francisco Maldonado Torralba, who has already contributed to our activities and workshops. But today we have been here physically, so it's very nice. We are progressing as a society. So he's coming from the University of Cape Town in South. He's going to tell us about dark matter candidates from Northern. Yes.
Thank you very much, Gonzalo. So hello everyone here and hello everyone online. It's a pleasure to be here finally presentially. So I want to thank the organizers for inviting me here and letting me present my work, which in this case is about a dark matter candidate that appears naturally from torsion theories. But before going into this specific candidate, let me justify why we want to go to modify theories of gravity. Probably in this audience, I don't need to justify, but it's always good to remember why we do what we do. So if we have a strange measure in nature, we always can follow two approaches. Either we assume that there is some unknown matter or energy that is affecting that measure, or since the theory is no longer validated by experiment, we can assume that it's incomplete. So we need to modify it and extend it to the energy scales that we're working with in that experiment. So we have many examples of these two approaches in all the fields of science, but it's good to focus on the problem that we have now in cosmology and gravitation, that it can be resumed in these three aspects, that it's the accelerated expansion of the universe, the rotation curves of galaxies, and the tensions that exist in the cosmological model that we use to explain both of those problems. So right now in gravitation, we're following the first approach of the two I talked to you about, that we assume that there is some strange energy and some strange matter that explain the problems that we have. In the case of the accelerated expansion of the universe, we know from the 90s that the universe is not only expanding, but it's following an accelerated expansion. So we introduce a new form of energy that we call dark energy because we don't know exactly what it is, and it is usually encoded in the form of a cosmological constant in the field equations. And in the case of the rotation curves of galaxies, we know that with general relativity and baryonic matter, we cannot predict the rotation curves of galaxies. So we need to add a new form of matter that we usually consider that is called dark matter, that explains that rotation curves of the galaxy. So if we add the two things, that then the lambda and that one the CDM, we have our preferred cosmological model that is lambda CDM. That actually works pretty well, except for these tensions that are appearing now between the early and late measures of the Hubble parameter. So we have followed the first approach, that it is adding this new energy or matter, and we haven't detected dark matter yet. We don't know what it is. We don't know exactly what dark energy is yet, and our cosmological model suffers from some problems. So why not follow the second approach until we have some measures that let us decide between the two? But we are entitled to go to the second approach that is to modify gravity. But how do we do it? So we go to the gravitational action, that is the anticellular action, and modify it somehow. But we rely on the Lovelock theorem that I don't know it by memory, so I'm going to read it without shame. It tells us that the only possible local gravitational action, which contains only second derivatives of a single four-dimensional spacetime metric, is the Einstein-Hilbert action. So if we want to modify the Einstein-Hilbert action, we need to break one of these assumptions. So we can, I don't know, consider extra dimensions, higher derivatives, give up locality, or just add more fields, and that's all. You can choose one of these approaches, the one that you like the most, but you have to be careful with a few aspects. First, we need to make sure that the theory does not exhibit instability, because if we want to explain nature, if a theory is unstable, we are not able to explain what's going on. Also, of course, because we are doing physics, it needs to be compatible with current experimental measures. And finally, this is more theoretical, but we need to justify where this breaking of the Lovelock theorem is coming from, because if not, we are just parameterizing or ignorance with some parameters. And the theory I'm going to choose is Poincare-Gates gravity. That is a theory that is quadratic in torsion and in curvature. And I mean, they're all familiarized with torsion, but just in case, I'm going to tell that it's the antisymmetric part of the connection, which in GR is choose to be symmetric ones and to have no symmetricity. And this theory is called Poincare-Gates gravity because it can be obtained naturally following the gauge procedure of the Poincare group. You take the Poincare group and you promote it to a local symmetry, and then the Riemann tensor appears from the Lorentz group, like the field strength of the Lorentz group, and the torsion tensor appears from as the field strength of the translation group. So why go beyond the Levi-Civita connection? Why consider torsion or non-metricity in some cases? And the thing is that general relativity is not the unique interpretation of gravity. There are physically equivalent theories that we saw yesterday, as for example, the parallel gravity, that you can build an invariant from a connection with no curvature and non-metricity, also set to zero. You have coincident general relativity, in which you have zero curvature and zero torsion, but non-new non-metricity. And also you can build like a general parallel theory also that has torsion and non-metricity and zero curvature. And you can prove that all these actions are the same up to a total derivative, so they describe the same. So this means that there is no physical reason to choose a certain connection. We just choose the Levi-Civita connection because it's simpler mathematically speaking, but not because we have a physical reason. And also, I think it's good to consider torsion theories because it has like a specific signal that it has a coupling with the internal spin of fermions. So you have measurable effects. If you study fermions comparing it to other particles, you're going to see effects that are coming from torsion. So you already have something there to explore and see if your theory works or not, or set constraints and this kind of stuff. So as I said, we have the Riemann tensor coming from the Lorentz group and the torsion tensor coming from the translations. And as it is usual, when you follow the gauge procedure in Yang-Hill theories, you take the up to quadratic term in the field strengths and you can build this. But I mean, as you can imagine, this action propagates a lot of degrees of freedom. And apart from the usual graviton, this propagates two massive spin 2 fields, two massive spin 1 fields, and two scalars of different parity. Bad news is that not all these propagated degrees of freedom are stable, and actually only the two scalars of different parity survive when you study the stability non-perturbably. And the good news is that, okay, we have 2 degrees of freedom. We have the graviton and we have 2 degrees of freedom. So why not try and describe the problems that we have in gravitation and cosmology with these extra degrees of freedom that we have in the Poincare gravity action? So when you take all this stability argument into account, you end up with something like this, that it's the Ricci scalar plus the torsion square terms plus this Ricci square term that accounts from the scale for the scalar, and this whole square term, the whole is there here, that accounts for the pseudoscalar. And you can see that this term is characteristic of torsion theories because this term is 0 in general relativity. So you cannot have a whole square term in a metric theory. So that's why we're going to study these pseudoscalar degree of freedom and these scalar degrees of freedom, but for other words. So if we set beta to 0, we have the whole square theory, and you can introduce, well, you can do some transformation and introduce an auxiliary field as a Lagrange multiplier, and also take into account this interaction with the internal spin of fermions via the axial current that I told you about. That basically in torsion theories, if you take the minimal coupling prescription, you have a coupling of the axial currents of fermions with the axial vector of the torsion, that is the total antisymmetric part of the torsion. So, I mean, if from here you add this term also, and you take into account the field equations of the axial vector of the torsion and the trace vector, that is taking the trace part of the torsion tensor, and then you integrate those fields out, you end up with a Lagrangian in which you can see the pseudoscalar. It's still complicated to see. We will simplify it, but not simplify it, I'll complicate it a little bit as well. But yeah, you can see that you have a pseudoscalar with a derivative coupling with the axial current. So okay, from here you say, okay, we have a pseudoscalar that has a derivative coupling with a certain current. And you can go to the particle data group review and go to action-like particles. And the definition of an action-like particle is a pseudoscalar which has a derivative coupling with a certain current. So we have an action-like particle. So we know that action-like particles can act as dark matter candidates. So can we explore which are the conditions for this pseudoscalar mode to explain dark energies? Yeah, the thing is that if we want to consider it as a field, we need to take into account the quantum corrections because, I mean, for example, here, okay, we have a derivative coupling with the actual currents of fermions, so we can expect for dark matter particle to collide and then have like an electron positron. But an electron positron can collide and then have photon. So you know that when you take into account quantum corrections, you should expect an interaction with the electromagnetic sector. So that's why we need to take into account that couplings to the standard model that come from quantum correction, and they appear from the fact that the actual currents, when you take into account quantum corrections, is anomalous, and now it appears in curved background these two terms. One that is this electromagnetic tensor, which is with its dual, and the Chern-Simon term. So if you make integration by parts to take the anomalous part of that current and just have the non-anomalous part, and then the other parts here written explicitly, and you canonically normalize the Z scalar to have this kind of kinetic term, and go to the weak field limit. That actually it's a good approximation, because if the field is bounded, you can always choose the parameter mt that we have here, such that the weak field limit always here. So it's good, and the thing is that if you look at this is the action, the usual action of an action-like particle, or even an usual action. But it has new terms, that is this one, the Chern-Simon terms, that usually should be present in usual actions, but since they are usually working in cosmological context, the Chern-Simon term is zero, so don't usually consider it. And we have a form-fermion contact interaction that is usual for torsion theories. So we have a particle that can serve as dark matter because it has the form of the usual action, and also we have extra terms that are going to allow us to differentiate it with the usual action, especially this form-fermion contact interaction. That it's a signal of torsion theories. If we see this kind of interaction, it could be a nice signal of having these torsion modifications of gravity. And also, if you want to know details about this model, you can go to the recently published article in the archive, or you can ask me in the coffee break. So, okay. So as I said, we need to be careful when we modify gravity. We have said where this modification comes from is following the gauge procedure of the Poincare gauge group. We have checked that this mode is stable, and now we have to take into account the experimental constraints that we have on this scalar. So from the form-fermion contact interaction, there are many experiments in particle physics that study this kind of interaction and if it appears or not, and they set constraints on the constant that you have in front of the interaction. So we translate it into a parameter space, which means that ms has to be greater than this value. Also, from the Chern-Simon term, we have constraints also that we can translate on our parameter space, but they are much lower than the one coming from the form-fermion contact interaction. And also from the coupling of the axial currents, we have also experiment because this kind of coupling appears in action. Actions are very studied in the literature, so that's fine for us because we can use those experiments. And it tells us that ms needs to be greater than this, but only for a very limited mass range of for action. So okay, this is much better, but only for a mass range that it's very low. But the good thing is that we have another experimental constraint, that it's the coupling to the electromagnetic sector, that it's the usual constraints that we have on action-like particles. That basically from this kind of coupling with the F-mu dual, if you have that action-like particle traveling through a magnetic field, you expect that it transforms to photons and then back again to the action-like particle, and then to photon, action-like particle, photon, action-like particle. And you can measure this kind of behavior, measuring photons, that it's easy. Well, easy. And setting constraints on this interaction between the action-like particle and the electromagnetic sector. We have, for example, telescopes that try to measure these action-like particles coming from the sun. We have oscilloscopes that are the ones that try to measure action-like particles coming from the center of the galaxies. We have measures from all the galaxies to see the excess of gamma rays that we get from those theories, and also some telescopes like PIMOS or MUSE. And also we have a very good constraint, that it's the horizontal branch stars, that you study the difference in ratio between the horizontal branch star and red giants, because if you add action-like particles, you expect that this ratio is going to change, because these red giants don't produce action-like particles. So, and there is a very good theoretical theoretical limit due by people by the University of Granada, that it's quite nice. So yeah, I mean, you see that the parameter space still has a lot of free space. We know that all the part that is below here is constrained by the four fermion contact interaction, and this is quite constrained in this part. I mean, this is a double logarithmic scale, so it is quite a big part of the parameter space. And you need to know that these diagonal lines, let's say, this is constant mass, let's say. So this coming here is, this is greater mass, and this is lower mass, let's say. And the lines of constant mass are these horizontal diagonal lines, let's say. But this is translated into a parameter space of a theory in terms of ms and alpha. So what happens in this region, the one of lower mass or higher mass? For low masses, we have Lyman measures that tell us that or dark matter models cannot have the mass lower than 2 times n minus 20 electron volts. That seems reasonable. And for large masses, we need to take into account the fact that if for a dark matter candidate it's too massive, it's going to disintegrate, and then that disintegration can give us rise to new light elements, but not new ones, but it's going to affect the abundance of light elements. So we can set constraints with that fact. So for large masses, the parameter space is even more constrained in that part. You need to add this triangle. And this is also a double logarithmic scale, so it constrains a lot. And we know that also all this part here is constraints. So, well, yeah, we can use this part here. Or we can, especially this part as in usual. So, one final thing that we need to take into account is that this pseudoscalar can account for the abundance that we have for cold dark matter. And how do we do it? Well, we need to take into account how these action-like particles are produced, which is usually by the misalignment mechanism, that it's based on the fact that the value of the field at the end of inflation is not at the minimum. So it reaches a point of the expansion. I mean, if you imagine the equation of a scalar field, you have it's like a damped oscillation, let's say, that it's mediated by the Hubble parameter. So when the Hubble parameter reaches a certain point, it is not overdamped anymore, because for very large Hubble parameter, of course, that oscillation is going to be overdamped and it's not going to roll that scalar field. But it reaches a point that it starts oscillating, and that coherent oscillations give rise to these particles. So, taking into account the fact that the predicted abundance of dark matter is this one from Planck, we can exclude a lower region with respect to the value of the field after inflation, that is called the misalignment angle, and with respect to the mass of the action-like particle. So if we somehow could know the value of the field after inflation, that probably if we choose a certain specific model and we can constrain it somehow, the initial value that we can have, we will know the allowed masses that we have in order to explain all the cold dark matter. And also we will know all the masses that are excluded from overproduction of dark matter. Because we know that if we are here, okay, it's not constrained, but our dark matter candidate cannot explain all dark matter. In order to explain all dark matter, you can only stay on this red line. And actually, this red line is much smaller than the one painted, because this is a double logarithmic scale again. If I painted this actual line, it will not show up. So for illustrative purposes, you have it there. And basically, what I wanted to bring home as a thought is that the new degrees of freedom that we introduce in modified gravity can be used to model dark energy or dark matter, or whatever you want to solve in this case. And that in this torsion theory, that is Poincare gauge gravity, the pseudoscalar degree of freedom can account for all the predicted cold dark matter, even if experimental constraints are fulfilled.
Thank you so much for your talk. So, we have a question from the chat. So you can read it if you want. You can read it.
We have needed the theory C. We have no extra fields. But in the case of coincident general relativity, it's just it's the same as general relativity, because when you write the action, you have something that it's I mean, you can always do a transform. If you have a connection that is different from Levy beta, you can always write Levy beta plus of non-metricity. So if you do the transformation back and write your action of the coincident general relativity in terms of the Levy beta connection, you end up with the Ricci scalar plus total derivative term. So it's a theory that does not have extra fields. It's no, I mean the theory that it's general relativity. It doesn't have extra fields. We don't need any. I mean, we don't expect anything new because it's same as general relativity.
Okay, so I'm going to he has answered your question. Any other questions? Oh, here. I wanted to ask you like that. There is a way to reduce in very kind of theory the generalization you observe, I mean, the Neanderthal. And this question is somehow related to the fact that you have in this theory two time scala, no? The odd time scala and the even time scala.
Mhm.
So when you just use the Euler, when you solve for the raised part torsion and the axial part torsion, these two types of scalas couple. Instead, when you use the Indian term, the raised part, for example, depend only on the even part scala and the axial part only on the odd part scala. So there is a way or not?
There is a way to consider the two, the scalar and the pseudoscalar, and I mean the R square theory and the whole square theory, and you predict an interaction between the scalar and the pseudoscalar. That's what you mean.
If you can go back to slide, and you write the effective yeah.
This one? Yes.
I mean, when you perform the calculation in effective theories for quantum gravity or quantum gravity square models, you can rearrange the kinetic term from the scalar model in a simpler way. Usually, the denominator disappears and just increases.
Yeah. You can canonically normalize in order to be in this way.
But the Neanderthal term naturally produces this type of normalization. Just this plot that you have to do some stuff.
Yeah. In the case is that the Holtz term is the one that appears in concurrent gravity. It's true that you can make modifications of Einstein-Cartan, for example, that are inspired in loop gravity that take into account the Needham term, and you end up also with an action-like particle that is similar to this one, but following another approach. Like this approach of the Needham term was considered in the 2000s by Mercury. So yeah, this approach has been used, like the Needham term, but as an extension of Einstein-Cartan. In this case, is to study a certain degree of freedom that you have in a theory. We are not studying.
Poincare theory does not produce this type of just the.
Yeah, it appears the Holtz term, not the Needham term.
Any other quick question?
Well,
Thank you.
So I was wondering, when you included the coupling to the fermions to the Lagrangian, I was wondering, after that you mentioned about quantum corrections, and my question is that where do they come from, or I mean, are they added by hand, or you have another better action from where they arise?
Like the quantum corrections for the axial current, or?
Yes.
Yeah, the thing is that in the classically the axial current is well, in the case of massless fermions, it's conserved. In the case of massive fermions, you have a relation with a part that well, you have a certain relation. But when you take into account the quantum corrections, then that conservation of the axial current does not behave the same. So you have these extra terms here. This is known as the axial anomaly, that when you take into account quantum corrections, that you have extra terms to
But that's the question. How do you know what are the quantum corrections from what theory?
I mean, it's from the actual anomaly. It's called. It's from quantum field theory, and also taking into account the curved background. So it's from curved quantum field theory.
Okay, thank you.
Okay, so the other question. Okay, thank you.
Yeah, no problem. Thank you.
Thank you. Thank you. Está aquí, ¿no? ¿No? A ver si no lo ven. Sí, nos lo han mandado PDF, pero no sé si lo han metido ellos o no. Si no lo tienen en el PDF. Aquí no la ves, ¿no? No, no. Vale, tengo yo. ¿La tienes? Ah. Es que no te digo que ahí no tiene nada. Pues tienes el pendrive de su vamos antes. Dejo el pendrive y ya está. Bueno, vamos aquí. Hay una descoordinación aquí. Claro que si quieres es más rápido. Imagino que ya. Okay, so our next speaker is Paulo Amaro Sebane. He's coming from the several places, but the university, the Polytechnic University of Valencia, right? And he's a well-known expert in gravitational waves and other aspects. And he's going to tell us today about how small black holes and black holes interact.
Okay, right. So yes, first, I don't think I am an expert on anything. So this is going to be maybe I have tried to give you a context of it because I know that you don't do a warning. I actually graduated here 21 years ago, and I know what kind of things are going on. And I have tried to do something very general. We don't have to go into everything, but the something interesting happened because I was step by step. Well, just as a kind of fun note, I have physics, and I always like to point to this. So when you consider the total power output of two stellar mass black holes merging, like the two stellar mass black holes. Than 50 times all of the stars in the whole universe. I am cheating. We're talking about power. And when you talk about power, talk about time. By this very small quantity over here. So that if you want to look at the real energy, but still it is only, in quotation marks, it's like taking 3 suns and putting them into, and this is what you have. Now, this is equivalent to about 5,000 supernovae in this strange unit to the power of 51. So you have 10 to the 54 tera electron volts. Now, this is for the kind of for instance, for 10 to the 8 so masses supermassive black hole, we're talking about 10 to the 60 tera electron volts. Anyway, so I'm going to the difference in the gravitational pull onto points which are diametrically separated is going to be so huge that the star will be distorted from being something spherical to something ellipsoidal. And if you get close enough, it will be enough to disrupt. So you really destroy the star. Now, imagine that this is change the length of the orbit constantly, like this, right? So you have a burst of gravitational radiation here. So the number of cycles that you have in band is proportional to the mass ratio. So you have a small black hole with a mass of 10 solar masses here, and a supermassive black hole with a mass of 10 to the 6 masses here. You have 100,000 cycles before the small compact object plunges into the supermassive black hole, right? So that you have imagine that you have a camera taking pictures of a space-time of what warped space-time is around a supermassive black hole. So what you de facto are doing is a cartography, a mapping of a space-time around a supermassive black hole from an area in which you cannot get any kind of information with light, because it is impossible to get it with light. Now, why is that important? Well, that is interesting because you get to explore a place which is forbidden to horizon. Relativity. The singularity, which is a complex, a fun word to say, I don't know what happens here. That's a singularity. Now, the point is that this, but the point is that it's not like a, probably you have seen all of it is exploding, are giving birth to the because the reason of space and time. That's a point where and so it is a much more subtle matter than having a point in space-time, which is in the case of a Schwarzschild singularity, it's not that. It is actually a time. So you can define you say that space-time is singular if it's an extendable. But anyway, I don't want to go into this case. But the point is that what happens beyond that is anyone's guess, because you're talking about you may so in any case, we have three conditions for having singularities: possibility of energy, causality. I'm going to assume, if you assume these two things, that matter fields must obey a certain kind of energy condition, a causality, so that you're not moving fast on the speed of light. Then, if you have an event horizon, you must have a singularity. That's why Penrose got his prize, right? So you can see a link between event horizons and singularities. It's a kind of indirect way of recovering information about the singularity that you have thanks to the event horizon. And the kind of gravitational wave probe I want to talk about is the best way, is actually the only way that we can explore the event horizon. Oh, by the way, this is something that I guess the only mathematician here is Pep, sitting back. But there is a very interesting connection between geometry and topology, because you know that the integral of the curvature of a manifold is true by the Euler characteristic. So that means that you can link topology to geometry. If you get information about the geometry, and you get one kind of geometry, thanks to the Gauss-Bonnet theorem, you can link the two of them. So when looking at a problem which involves, of course, astronomy, I hope this is enough motivation for you to be interested by this kind of source. So, stream acceleration styles. This is what I just described. Imagine that. So this is this is a movie, by the way, by a friend of mine, Steve Grasko. We can find it in the internet, I guess, and YouTube. But the point is that you can see what I was describing before. You have a supermassive black hole, and you have a kind of orbit, if you want, which is not Keplerian. You are changing the inclination, you are shrinking over time, and of course you have precession around the supermassive black hole. And that you can actually prove, that you're going to completely fill up space, phase space in the shape of a torus. So that the small black hole or the small compact object, neutron star, whatever, is filling completely space-time, exploring all possible positions around the supermassive black hole. Each of these bursts is sending you a lot of, by the end of snapshots of space-time, so that you can start to actually test and run, tests of alternative theories of gravity, like Chern ions. But the point is that, and this is a very important point, I think I can manage to explain everything. The event rates are very, very low. And now you should ask me, what kind of event rates are you talking about? And this is where a little bit We cannot prove that it's a dark hole. So the event rate, if you calculate how long or how many black holes, small black holes, are merging with the supermassive black hole at the center of our galaxy, this is the kind of number that you get. 10 to the or 10 to the minus. This which you switch on Lisa, you have one of these at the galactic center. But that's fine, because we can go out to distances as huge, distances corresponding to a redshift as large as 1 or being extremely optimistic 4. And you have millions and millions and millions. Millions and millions and millions times 10 to the minus 5, 10 to the minus 6, you get a decent number a year. So, yeah. So these things are called extreme ratio because right? This is why we call them EMRIs. So they have you can do with them. These are very strong. I mentioned this already. General relativity is a theory. The world lines, the orbits of EMRIs, extreme acceleration spirals, they provide you with a geodesic mapping of the space-time. We're talking about the black holes here. And this point is extremely important for astrophysicists because the parameters associated to the ridiculous mass with an error between 1 and 0.1%, and you can measure the redshifted spin of the supermassive black hole with an error as small as 0.1 or 0.01%. And the most interesting thing is that this is a direct reading without any kind of modeling other than general relativity. The only assumption that you do is that general relativity is a correct theory, and that this is how you start the parameters. So this is quite impressive. Okay, so all of this is very fun and wonderful, but the point is, can you actually measure them? Can you that we can do that. There is this mission, I don't know whether we have heard about this, but it's called LISA, which is the Laser Interferometer Space Antenna. We have a triangle, and in each of those satellites, we have a free-falling mass towards Earth. And you have a laser beam constructing actually two interferometers, two orthogonal interferometers, with an arm length of 2.5 million kilometers and a resolution of 10 picometers in those 2.5 million kilometers. Now, this is an ESA-NASA mission, and on June 2017, we actually got the clearance goal from ESA. Now, if you think in terms of technology, this is extremely complex because you have a free-floating thing, you know, and the other mass. You have a satellite, and that satellite is shielding that mass from, you know, cosmic rays. You know what cosmic rays are, of course. Solar flares, etc., etc. But at the same time, the satellite cannot touch the mass, because if you touch the mass, you are deviating the geodesic. So from a technological point of view, this is extremely challenging, to the point that we cannot go to ESA and say, listen, I need 1,000 million euros for doing this experiment. Look, it's very nice, but does it work? But I don't know, let's try. No, you cannot do that. And in the past, I used to say that this is so expensive that it corresponds to 2 Spanish football leagues. And so one day I actually checked and I was wrong. It is half of one. So, it turns out that if you just take the we can not. Anyway, the point is that the money is on the table now. So why, besides Nobel Prize, because 10 years ago nobody cared much about gravitational waves. Nowadays, a lot of people are interested in gravitational waves because that Nobel Prize, we have LISA being founded, etc. But anyway, these are very good news. And so yes, because it's so expensive, ESA required this is what they did, because I didn't do this. A group of very clever this is what you see here, these strange units, is differential acceleration measurements as a function of the frequency. Now, over here, you see the requirements by ESA for the LISA Pathfinder. This is the way they gave it. They gave to the mission, to the LISA Pathfinder. And when they launched the satellite, they were over here. So about, depending on the range of frequency, about say 1 order of magnitude, or maybe even almost 2 orders of magnitude. And almost 1 year later, in February 2017, this is a kind of sensitivity that they had. I'm very surprised because well, we were supposed to be over here and we were here, getting to 10 to the minus 15, while they were asking about this, right? And by the way, this is the full LISA mission requirements. And notice the LISA Pathfinder, which is a shrunk version of LISA, that sensitivity than LISA. Anyway, so and that again, would you? So what? Yeah. So okay. That this is the case. But what about I don't know objects which are compact enough so that they don't get destroyed when they get very close to the supermassive level, right? And then I thought of a superstellar object is, for instance, a brown dwarf. A brown dwarf is a failed star. It's a star which is much more massive than Jupiter, but without enough mass, to start the thermonuclear reactions, etc. It's a piece of rock. Okay, and then I did this plot just for the minimum mass that a supermassive black hole must have, so that any kind of object with these masses, this is 10 to the 2, this is 10 to the minus 3, can cross the event horizon without suffering tidal stresses. So that, for instance, if you look at this line over there, that corresponds to a red giant of 50 solar radii. And that means that if you move to the left, for instance, a supermassive black hole with a mass of 2 times 10 to the 9 would allow a red giant to cross the shape of the curves is just so they have this strange shape because I was using stellar models which give you the link between the mass and the radius, and they are complex. This blue line over here corresponds to main sequence stars and brown dwarfs. And this arrow over here is the black hole at the galactic center, which has a mass of 4 times 10 to the 6 solar masses. Okay, so you draw a horizontal line, and you can see that masses, that masses between these and that can plunge, can cross the event horizon in our range of masses correspond mostly to brown dwarfs. I said, okay, so what if humanly, what if we had one of those at the galactic center? So this is the kind of signal follow what so LISA in principle is meant to last at least 5, 8, 10 years, but let's assume 1 year only of observation. Forget about these lines, these dashed lines are just the contribution of different harmonics, just forget about them. And look at the solid line, this solid line. And this is the time to plunge. This is 100 millions before the small stellar black hole crosses the event horizon. Sorry, the brown dwarf crosses the event horizon. This is 10 million, 1 million, 100,000 years, etc. So you can see that already a few million years before plunging, before crossing the event horizon, our source has already a signal-to-noise ratio which is detectable, because I am assuming a threshold of about 10. But as time goes on, say a few thousands of years before that moment, you're talking about signal-to-noise ratios of hundreds. If you get closer and closer to the plunge, you are talking about say, 8 to the 4 years before the plunge. We're talking about thousands in signal-to-noise ratio, and from that point, approximately, which is say hundreds of years before the plunge, we are talking about 10 to the 4 in signal-to-noise ratio. Now, of two expected $5,000. That you had one. Have a different example, but again, in this case, we're getting even to 20,000 in signal-to-noise ratio. Okay. This is well, probably this. So this quantity over here, HC, is how much you can, expand or contract the ounce of the detector by a gravitational wave divided by the length of the gravitational wave, so that it is dimensionless. So we're talking of 10 to the minus 18, 10 to the minus 22 in 2.5 million kilometers. Okay? And this is the frequency. This is the sensitivity curve of LISA, right here. And this is the gravitational wave associated to sources that focus on that harmonic because it's the dominant one. And that point over there, I don't know whether you can see it, but this is 5,000 years before the moment in which the brown dwarf crosses the event horizon. And this is 1 year before that moment. So that you need 5,000 years to cover that, that beam of frequencies. You need 5,000 years to cover that. And if you move to the left, it is worse and worse. So you have a source which is going to spend millions to move extremely slowly. If you take millions of years and you consider that LISA is going to only live 10 years from, and we're going to die after 80 years, maybe, you have something which is fixed in frequency. You don't see it moving. You will move an epsilon, but you will not see that. So it is contrary to black holes. Range of frequencies in about a few months or years, but we are going to spend millions of years to cover this, and that's because that's because the mass ratio that we're talking about is of about 10 to the. Why I call these things extremely large mass ratio spirals, because in the case of a stellar mass black hole, remember, you have 10, you have 10 to the 6, you have a mass ratio of 10 to the 5, 10 to the 4, maybe, I don't know. But if you're talking about 10 to the 8, which is huge. And this solving the two-body problem in general relativity for mass ratio. So that the mass ratio like a the 78 kind of know how to solve for a Kerr black hole. Okay. So, and yeah, and that's because that action is reaction depends on that mass ratio, and in this limit, you're getting very close to a standard geodesic. Okay, you have similar, so that they are perfect, and they are, so you just look at the data. But this, as I have coined them, XM rays, we have synchronous ratios as a Western view, which could be problematic because yeah, but the question is, okay, this is wonderful. That close to the supermassive black holes, and I'm going to ask you for a leap of faith, trust that these results are correct, because what this has been. I want to just flash you to the last slide. I don't want to show you all of these calculations. See, this is the final equation, but anyway, it has been published. But in any case, but the nice thing is that another person after me did a similar calculation and we got similar numbers. But anyway, so look at that axis. This is the event rate times 10 to the -3. And this is just the inclination of the orbit and the spin of the supermassive ball. But forget about that. Let's look at that number, right? You are talking about something which is 0.5, 3 times 10 to the -3. So it looks like a year. About the event rate. What we mean is you have to wait until the small thing, the small compact object, the small brown dwarf, is that before that moment, which is a very peculiar moment in evolution, we have had 1 million of years in band. So that, as you can see, what matters is not the event rate, how many of these will be crossing the event horizon, but how many of them are going to be in band. Yeah. And again, just to give you an idea of what is going on, this is less characteristic strain. So this is delta L divided by L. This is the Lisa sensitivity curve, and this is the frequency. And these are isochrones. And different points in that line are contributions of different harmonics. Forget about it. So this line corresponds to an isochron for one of those X angles, 10 to the 8 years, 3 times 10 to the 8 years before the merger. But you can see that this is slightly out of band, right? But from this moment onward, so for instance, this isochron is completely in band. And this is again 10 to the 8 years. This is 10 to the 7. This 10 to the, what? I don't see, yes, 6, 5, 4, 1,000 years, 100 years. So you see how slowly this thing is moving, is progressing in frequencies. So what matters here is not the event rate, but the event rate times the amount of time that you spend in that. Sorry. So we have seen that the lifetime is up to 10 million years, but actually for the numbers I took 10 to the 6 years, trying to look for the minute for not trying not to blow up the numbers. And the event rate is about 10 to the minus 3. So the number which matters is this times that, which gives you 10 to the 4. But not all of these are going to contribute, and I don't have time to spend it. Why? But just this briefly. It depends on the same matrices. But in any case, because we have the event rate, so this is the relative fraction expressed as a line density, which is the variation of a number of sources that you have as a function or depending on the same matrices. We have a flux. Well, this is just physics, right? We have a flux of things coming here. This is the maximum. This is kind of a place from which you know that those sources can turn into real sources, contributing to the detection. This is the same matrices which defines the number of sources that you will have in band. At the beginning, between this axis and that axis, the sources are going to be very eccentric, but they will lose angular momentum because this is what the gravitational waves do, right? You lose energy and angular momentum. So that even if they are very eccentric, and I didn't explain why, but I can do that if you want. Even if they are at the beginning extremely eccentric, they will become similar until finally they will match with the supermassive black hole. So you have a flux, you have continuity equation, so you can derive the relative occupation fraction. You have the boundary conditions, so you have the total number, you have the boundary conditions. You can define the different thresholds, so you can derive the occupation fractions. And in this area, before they get in band, you get those 10 to the 4 years. The very eccentric orbits, you have about tens of them, say 40, and that circular orbits, you have 30 of them. These are the sources which have C-naught ratios between hundreds and thousands, and over here you have between thousands and tens of thousands. Okay, so conclusions. These eccentric, which are extreme mass relation spirals, I call them just extremely large mass relation spirals. They are extremely loud, with C-naught ratios of up to 10 to the 4, so that you can detect them very accurately, of course, and you can extract parameters with a very, very high precision. And the question is whether these C-naught ratios will turn out to be a problem for the detection of binary or supermassive black holes. Talking about mass ratios of 10 to the 8, so that back reaction makes life easy. You can model these things very easily without supercomputers, without all for what we would require for smaller mass ratios. We have just a geodesic. And I didn't mention this, but the analysis that I did is a statistical one, it's a steady state one. So that at any given moment, like today, 100 years in the past, 1,000 years in the future, we have at any given time this number of sources in band, tens of them. About 30 of them with C-naught ratios between hundreds and up to 20,000, and about 40 of them with C-naught ratios between tens and a few hundreds at any given time. And because of the large C-naught ratios, as I said, we can see these examples for nearby galaxies, not only in our galactic center, but in nearby galaxies. Anyway, so I think this was enough.
Thank you, Pau, for this very interesting talk. So, anybody has questions or comments?
Yeah, thank you for the talk. So I was wondering, is there any physical reason why the signal to noise ratio saturates with time? So when we were plotting the signal, the SNR function with time,
Yes.
it was reaching 10 to the 4, and then it was saturating.
Yeah, that's a good question, actually. But from an intuitive point of view, this because it's the maximum from the source. You cannot get beyond that. And you reach it, that's actually an excellent question because you have this very sudden raise, and then it saturates very quickly, but with a nice property that 1,000 of years before launching, you have already reached the maximum. Because it is slow, it's evolving so slowly. It looks like it's very quick, but it's taking you millions of years.
I was wondering if it's connected to any physical process, or if there are no more brown dwarfs to be if you go backwards in time. I was wondering if there is any physics that associated with this saturation, like there were no more brown dwarfs.
It is, as you say, because because the interesting thing is that let me see how to explain this. So if you remember, like this blackboard, you have the signal demonstration here, for instance, and we have here the time, and you see that this was going up like this, and then as you say, it was saturated.
Yes.
Now, so the interesting thing is that you cannot solve the two-body problem in general relativity. You know that the two-body problem. We don't know how to solve it. We can solve the one-body problem, which you cannot in quantum chromodynamics. But anyway, you can approximate the two-body problem in general relativity, and when you do that, you see that the time scale for a binary to evolve because of additional gravitational radiation is proportional to the symmetry axis of the binary to the power of 4. What does it mean? This means the following. This means that if you have the evolution, trying to find a place where everybody can see it. If you look at the evolution of the symmetry axis with time, your binary will very slowly evolve, so that if you look at the variation in symmetry axis, it's 0 for a very long time until it really takes in this emission, until you have this sudden match, right? So that in a very short amount of time, we have a huge variation of the symmetry axis. While over this phase here, which we call the spiral, we have a very small variation of the symmetry axis. And that this is somehow connected to what you saw there. Okay.
Any other questions? And I have a question, maybe you can comment on that. The estimated population of small objects like brown dwarfs in the near galactic centers, I guess there must be estimations of brown dwarf production or generation. So they are taken into account in your estimation.
Yes, yes, yes. This is all of the part that I was asking for a little patience, but it was all of those slides that we didn't show because they must be extremely boring for you. I don't know, for backwards. Well, anyway. But yes, the point is that, well, anyway, the slides are there. So the interesting thing is that you might not know this because I didn't know it. I don't know most things. But when you look at the galaxy, about 25% of everything that you have in there, baryonic matter, is a brown dwarf. So 25% of the things that you have floating over there is a brown dwarf. Now, we have estimates about the density of brown dwarfs around our solar system, and we have theoretical expectations about what is the the occupation fraction of a brown dwarf as you get closer and closer to the supermassive cold. But the point is that it is not the number of them which you have, it is how they distribute around the supermassive black hole. And that's a very interesting problem, which goes back to figures 1972, how things distribute around a supermassive black hole. So this is density, the stellar density as a fraction of the radius. And what you observe is that you have a slope. At some point, you have something increasing with a power law, and you see this actually, you observe this, so that that power law is proportional to the radius to the power 7 volts. And that you can actually explain it analytically, which is very, very nice. And this is the reason, and that this is the way you have to, this is the tool that you have to use to derive the number of objects that you have distributed around the sequence.
So if these calculations are correct, then if you connect LISA, you are unable to do physically because it is completely saturated.
Yes, that's the interesting thing, right? Because these things are monochromatic. It's like, I don't know, you would go to a concert and you have a tenor going like,
But you have thousands of tenors with different frequencies.
not thousands, the final numbers are tenors. Still, you have not a tenor, you have a tenor with speakers to the maximum.
Different galaxies.
No, but because
You are taking into account
you cannot, so it is much more interesting. Sorry.
I'm trying to be pessimistic.
Yes, no, that's the point. You have to use pessimistic because otherwise you're just making noise. So the point is that, so first of all, we don't have thousands of them, we have tens of them. And because the signal-to-noise ratio is inversely proportional to the distance, so the signal-to-noise ratio is inversely proportional to the distance. Well, you can go, as I was mentioning in the conclusions, the closest that you can go is to M32, because it has, well, anyway, can go to M32. But you cannot go farther and farther away. But there is an interesting thing here, which might be a problem because of the following. So you have the supermassive black hole, and you have one of these small objects. And that is that you cannot do such a complete test of gravity with these x-angles because they are fixed. The parameters are not changing over time. You are not covering frequencies, they are fixed in frequency. But every 100,000 years, that supermassive black hole, we have a stellar mass black hole doing the thing that you like, going up and down, changing the plane, shrinking over time, etc. But at the center, we have something which might introduce a circular perturbation onto the orbit of the object that you like, to the point that you can actually completely destroy that orbit and lose it. And because the Milky Way is a representative galaxy for the kind of galaxies that LISA is going to see, you can assume that this is going to happen for all galaxies that LISA is going to observe. So that this problem will be affecting all galaxies in the LISA volume.
There are more questions in the audience, but I have to teach. Okay.
We have some problems with the audio, but Adrián.
No, I mean, this is not a question, and maybe it's not, I mean, it's kind of something that I was recently thinking about characterization of singularities. Maybe it's not the best place to talk about this because it might generate some little debate. But I will just leave the comment, and if anybody wants to discuss now or later, then I would appreciate that. I'm just saying this because at some point you talked about singularities and so on. And I remember that I want to discuss this idea with people. So for me, I was recently thinking about characterizing singularities as a failure to extend time-like or null curves. But I don't know, for people who have a geometrical background, this is like a strong notion. But if you think on particle physics terms, for example, in weak interactions or in general in the standard model, if you consider observers as particles as well, they actually disappear from existence when they decay or when they scatter with other states, and they just like transform into other states, which become the new observers, and then there's a new world line, if you want to think that classically. And there is no problem with that because all the things that are conserved keep being conserved, like the total energy of it's the same, the total charge is the same, So in some sense, I think that if singularities are always hidden behind horizons or something that can like make us think that this is maybe a state of the quantum theory itself and not only like a region of space-time. Maybe a black hole can be thought of a whole state, an unperturbative state of the theory. Then you could, for example, think of something in falling into a black hole, like a scattering process of, say, a photon and a black hole going to another black hole with a little bit more mass and angular momentum. And then from that point of view, the singularities are not even relevant. Either they exist or they not, because physically they cannot be seen. If you want to insist on what happens to the observer that goes into the black hole, well, maybe that observer just ceases out of existence because there's some kind of interaction process with a quantum state of gravity, which would be the black hole, and just turns into another black hole. I don't know, like I would like to hear like thoughts or on this kind of idea or way of thinking about singularities, because I understand that, for example, if you have Cauchy horizons, then I would be worried about this kind of things. But if you can always hit this stuff in states of the theory, which could be seen as quantum states, which could be interacting with what we call observers from the classical perspective, and then just give rise to another state, then maybe it's not such a big problem. I don't know if I was like, if I made clear my point, or maybe it was a bit messy.
It is by definition messy because it is very complex. And the problem is that I think that I have already killed all of them. And they want to have a coffee right now. But I don't know whether you can see my email. Can you please write to me so that we talk about this, or maybe I can listen to you better?
Huge mistake.
Huh?
This can be a huge mistake.
I don't. What's his name? Adrian? Yeah. I don't know whether he cared. Anyway, so.
I would say that if anybody wants to be included in the discussion, or just feel free, maybe you can write to Pau or to me. You can find my email online, but I think it's easier to write to him because his email is on the screen, and maybe we can make some kind of email group chat or something like that.
Yeah. Okay. I could be disappointed because I don't know anything about most things, but we can try it. Okay,
no, I mean, I will just write you maybe a longer email explaining my point, and you can answer. Okay.
Okay, so here we can have Pau again. You can do 15 minutes copy ready, and then we will proceed.
Te lo digo que todo el mundo lo verá.
¿Estás compartiendo pantalla? Sí, ya lo estoy viendo. Ahora descomparto. ¿Cómo se descomparte?
Paré la grabación, por suerte.
Ya está.
Bueno. Pues la señora Pablo no se va. Ahí. Sí, cada.
Ragazzi, il café con lui.
Es el tope de esta boquita.
No, pasa esa una locura de vida, ¿no?
Ok.
A ver, vino aquí.
No.
Ah, vino.
No, vale.
Hermano vino aquí. Ah, sí.
Giusto? No? Allora, se serve meno. We don't we feel limited validation rates that no. I mean, those cars propagate. So they're dispersive. What they do, but
I know they're propagating.
Así, la reunión.
Era una muy, pero que iban a el turno. Y al final yo pensaba
Are you mistakes that I would say something? I guess it's a good I had yeah, it seems that it happened that way. Even from last year that he was done, there is a it's strong. But this is the point in the you can suicide to go forward. It's very quick for me to prepare for all because it's already made when it's all done. Sí. Y
And so I'm staying here for this testing. Then go to this. So, I mean, you know, I wasn't so tired because it was a degree. Maybe it's better to avoid moving relationships and healthy. I had a big lesson,
Yo creo que estamos
No, I didn't have and there she can go start we have yeah, and you so I have to take cold words and
pero vamos a estar ya puesto para la peda. Sí, y y sigue compañero nuestro de toda la vida. Sí, claro, y soy sí, además ha colaborado un poco con
I'd say some of these that's one of the things. Los modos de boundaries and I mean, not necessarily developing theory, but applications to explain and analyze this theory.
Estoy jubilado.
It is
Esta televisión y luego voy a Italia con esto.
so you have the same person, that's it. Exactly.
No, pero en la Bellas de Lozones. También empezar con las sillas, en una copita, los 10 minutos
Okay, so our next speaker is Diego Rubiera, who is a researcher. In shadow observation as a form of new gravitational physics. So, Diego, whenever you want.
Thank you very much. I'm so happy to be here and see so many faces. There was a time when I was visiting this place 10 years ago, there was Gonzalo, a few students, and me, essentially, doing this thing. So I'm happy to see that the group has grown so large and the network collaborators. So usually, so this collaboration that I do with Gonzalo is about metric affine gravities. Many of you are working on this or are very familiar with it. But what I'm going to present today is not related to it at all. It's something completely different. And this is something that we started this year. So we entered into this field of shadows without knowing essentially nothing about it, just because it was interesting and we wanted to learn. So we started this with Gonzalo and Mercedes Herrero, who is doing a PhD with me. He's connected. Yes. And Diego Saez, also from collaborator from some people here. So the idea is to study shadows from a theoretical point of view. And the problem with this is that so there are many people doing this because of obvious reasons. So this is a trendy topic. So there are observations already working. There are observations planned for the future. And so this is going to be a tremendous source of data to feed our theories. So the idea is to check or to test alternative compact objects rather than black holes to see whether they can fit observations or not. And because many of these new compact objects do not arise in general relativity, but in other theories of gravity, so it's at the same time a test of strong gravitational physics in the sense of departure from general relativity. So that's essentially the idea. As I said, this all started with the shadow of black hole. So I'm going to explain what a shadow is. So, yeah. Okay, so this is the observation by the HT of the shadow of the black hole. And this is the numerical reconstruction of the signal you would be expecting to see. So this is the illumination of a compact object, supposedly a black hole, by this accretion disk by the plasma, who is superheated. There are many local physical and nuclear physics processes that affect the state of this thing. This is what you should expect to see. So more or less, you can see the rough details. More or less seems to something, right? More or less. So there are several concepts here: photon ring and inner shadow. I'm going to explain both of them because they play a very important role in the shape of the thing that you are expected to see. So how people do these simulations? So general relativity with hydrodynamical simulations, very complex stuff from the numerical point of view, which is fed with different things from the background geometry, in this case the Kerr solution of general relativity, a lot of feedback from the accretion-based physics, which is actually the bottleneck of these simulations, in the sense that the Kerr solution is very well known. There are many alternative compact objects from the Kerr black hole, but the part of the accretion-based physics is much less understood. So what people do here is just to get the numerical codes, start throwing assumptions into the codes, running simulations one after another, and then try to see what you get, and then compare with simulations to see what fits what you see. So this is the idea. Now there are two different things here. One is the light range, and another thing is the shadow. And there are actually two shadows: the usual shadow and the inner shadow. I'm going to explain. So the light range and the location and shape of the light range essentially depends on the background geometry, but the luminosity does not. The luminosity depends also on the accretion disk. At the same time, the accretion disk determines the shape of the different things of the shadow, luminosities, and so on. Actually, it's quite difficult to disentangle what is the contribution of each other. So so there are parts that are affected by the background geometry only, but there are other aspects of the observation that depend on the interaction with the accretion disk. Because this accretion disk physics is poorly understood, so you can see what the problem is, right? To distinguish whether you have modifications to the background geometry or it's simply that you are not having a well modeling of the accretion disk. Okay. So that's the problem with this kind of research. But at the same time, it's so interesting because you are getting a direct access to the strong gravitational regime of the gravitational interaction. So this is kind of physics that is not accessible to weak field limit tests, which is where we have tested relativity so well. So the central idea of this field is whether it's possible to disentangle those effects in the light range and shadow that correspond to the background geometry, whether Kerr or other thing, and which effects are due to the accretion disk physics. Okay, so this is the biggest problem here. So now I'm going to start with the analysis. I'm going to dismiss rotation. I will justify it later, and go to spherical symmetry, where things are much simpler to understand and actually reduce to the kind of problem that you have seen in a course of classical mechanics. Because the geodesic equation for a photon in spherical symmetric geometry, it can be written this way. But this is the typical equation you have in a motion of a single-dimensional particle, effective potential, which in this case has this form. So from a mathematical point of view, this is extremely simple to analyze. As you can remember when you were studying this kind of problem classical mechanics. So what you do is to characterize the potential in order to see, depending on the energy, whether the energy is larger or below the maximum effective potential. So there is a turning point, or the solution goes to the center. So this is something that is very well known for undergrad experience. In this case, the role of the energy is played by what is called the impact parameter, which is the key quantity characterizing the light trajectories. And among all the impact parameters that you might have, there is one privileged one, which is the critical one, which corresponds basically to the maximum of the effective potential, which in the case of classical mechanics, it simply corresponds to the circular orbit. In this case, the circular orbit is unstable because it's a maximum of the potential. And so when these conditions all hold together, you have what is called the last orbit that a photon might have around a black hole without being plunged into the black hole, right? So above, above the critical impact parameter, a photon will just meet the slope of the potential and some minimum distance from the black hole, it will be scattered back to asymptotic infinity. While for lower impact parameter values, then it crosses what is called the photon sphere, so the minimum distance that a photon can approach the black hole without being swallowed by it, and then they go to the event horizon. Okay, so this split your space of impact parameter values into regions. Those photons that approach a certain distance and then be deflected to asymptotic infinity, and those that are plunged into the black hole. Okay, so this is why this parameter critical impact factor is so important. So in this figure, it corresponds to what is called the photon ring. But now, there is something that first sight seems inconsistent because there should be no light coming from inside the photon ring, because those photons that come from asymptotic infinity, they'll cross the photon ring region and go to the horizon. So nothing could come out of the photon ring, but if they come out, so there is light being emitted from the region inner to the photon ring. Okay, so this has to be because we are only analyzing the background geometry until now. And it has to do with the physical application of this. I will introduce. So, okay. So from the point of view of the background geometry of characterizing the possible light trajectories that you might have and how they are going to contribute to the optical appearance of the object. So what you do is to write the geodesic equation in terms of the derivative with respect to the azimuthal angle, this way. And then, so for a given impact parameter value, you can integrate, not analytically, but mathematical or mappable, whatever, this equation to see what is the deflection angle of the trajectory. Okay. From a particle point of view, and for this problem, you are not interested in all lights on the sky, how they are going to be deflected, because you are only interested in those light rays that have reached you, that come to your screen. So what you do is solve this equation by backtracking it. So instead of starting from asymptotic infinity, a light ray that comes to you, you get all light rays that arrive to your screen, and then integrate this equation back in time to see the point of the sky these light rays came from. So this is the idea. Okay. And why we do this? Because all light rays that didn't arrive to us don't matter to us for the optical appearance of the object seen from our point of view. We are only interested in those that came to us. Okay, so you integrate the equation back. When you do this, you have different kinds of trajectories, depending on how close to the critical impact factor value your light ray is. We know that by the very definition of critical impact factor value, a light ray equaling it will turn an infinite number of times around the black hole before reaching you. This is the very definition of a critical Q. Now, if you want to classify how many times a light ray turns the compact object before arriving to you, you have to split the values of the angle, the reflection angle, depending on this number of orbits around the object. Okay, and this gives you different types of emission. But here I'm splitting in 3 different kinds: direct, lensing, and photon. So direct is something that light ray just suffers some kind of slight deflection angle and came to you. Okay, and lens emission is something that it gave half a turn around the object before reaching you, and you can do this as many times as you wish. Okay, So depending on how many loops around the object you want. And why is this important? Because the contribution, the luminosity that you're going to see in your screen can be proved mathematically, analytically, that is going to be strongly dominated by the direct emission. So those light rays that have suffered a slight reflection angle. While all subsequent trajectories that have stored a number of times around the object are going to be exponentially suppressed in terms of luminosity, okay, as compared to the direct emission. Which means that your screen, the total luminosity is going to be strongly dominated by the direct emission with lower contribution for lesser and photon emissions and so on. So the more tones photon around the black hole, the lesser its contribution to the luminosity. Okay, for the sake of characterizing what you see. And also, all these kinds of direct emission is going to manifest in your screen as kind of light rings, concentric light rings that appear in your screen. So what you are expecting, according to this, is an infinite sequence of light rings converging to the critical curve that are exponentially suppressed in luminosity. So this is the idea. Okay. So in this thing, you are not seeing these light rays. And we are going to see why. You are only seeing the direct emission. Okay, so this is due to two different things that I'm going to discuss. Now, this is for the background geometry. How do you model the accretion of this? So this is where things become active. Under several assumptions, or very assumptions, so the emission from a finite size disk or some finite extension, so is described as a Goldman equation, where you have to fit this equation with several inputs, including emissivity, absorptivity of the disk, and so on. So there are several factors which are model independent from physics, astrophysics. So that has nothing to do with the background geometry of the space-time. It has to do with the physics of the disk. So what we do in the numerical simulations is to take a pool of assumptions upon all these constants and other properties, and then run your simulations and get images. Now, if you want to do it from an analytical point of view, so you cannot do that. You need to make some assumptions. So according to, it seems that according to people running these codes, that these two assumptions are quite reasonable, are good approximations to what you see. So no accessibility, not exactly true, and monochromatic emission, which is not exactly true, but it's a very good approximation. Now, another assumption that we make, and this is a strong one, is that the disk is infinitesimally thin. This is not exactly true. So accretion disks are not spherical, but are not infinitesimally thin. But this is a limit case that is much easier to treat. Okay. Actually, the spherical symmetric case can also be treated analytically without no problem. And actually, the difficulty is intermediate phase, where things are a bit more complicated. Anyway, to understand the start of light range, you start with this. So when you do this, so there are, so we are going to assume 3 different models that are frequently used in this modeling. And here the idea is, since you have a disk with 0 thinness, the only important parameter is how deep the inner edge of the disk goes to the center of the object. So in model 1, so the inner edge of the disk is very far from the horizon, is located in the innermost stable orbit for a time-like observer. In model 2, this edge is closer, it's actually located at the photon sphere itself. And in model 3, so we allow the disk to go all the way to the horizon. So these 3 models simulate different stages in the evolution of the disk. So imagine that the matter starts surrounding the object, and they spin downwards, losing energy. So they are getting closer and closer to the object. And then at some point, they are going to get to the ion horizon itself and be swallowed by the object. So by considering 3 different models for the same geometry, you are going to see how the evolution of the disk is going to produce you different images. Actually, for the HT observations, the relevant model is model 3, because they know that the matter goes all the way to the horizon. Okay. Now, another thing that you need to assume in these simulations is the emission profile of the disk. Because these 3 models only tell you where the disk start emitting, but not the profile. The profile you need to assume it. So you assume some things for the emission profile, but this is not what you observe in terms of intensity. There are 2 effects correcting the emission profile. One is the gravitational recipe, so is the energy lost by the photon trying to escape from the object. for spherical symmetry geometry is this factor a square of the geometry. And then there is another effect, which is associated to these three types of trajectory that you are getting. And these three types of trajectories are there because this is assumed to be optically thin. In other words, it's transparent to its own radiation. This is why orbits, photons that have orbited several times the object, can come to you. If the disk is not transparent to the radiation, a photon traveling several times will be reabsorbed by the disk. So they won't exist. So you need these trajectories to be there in order to predict this structure of waves. So this is included here. So you need to make all these evaluations for the three different types of trajectories we are considering, the direct, lens, and a photon wave. There will be more trajectories, infinite trajectories actually, but because of this exponential suppressing of the luminosity, so they are neglected here. Okay? So that's everything that you need to include in your model. Another thing is, okay, in order to implement this, you need some kind of code. So we built our code with Mathematica. Actually, it's split into two parts. One is the integration of the geodesic equation for a bunch of geodesics, depending on different values of the impact factor. And the info that you get from here needs to be uploaded into another part of the code with the modeling of the accretion disk in order to obtain the image of the object. So we did our own code. We don't have a fancy name for it. Everybody has it. We didn't coin it yet. We will do at some point. And then you need some model for the geometry. And then here you can already throw whatever you want. Boson stars, non-curved black holes, lava stars, wormholes, whatever you want. So it's quite flexible to attack different kinds of geometry. So as an illustration, I'm going to consider this. Actually, this will be r squared, or r singly arc of x, not arc squared of x. So this is Schwarzschild geometry, but there is a correction in the radial function where we extend the radial coordinate by some constant. So this is a model introduced 2 years ago by this paper. It's a good model from an analytical point of view, in the sense that it allows you to test what you could expect if you allow modification for Schwarzschild geometry. And because it contains 3 different kinds of geometry, depending on this parameter. Black holes or traversable black holes. But this is good. It allows you to compare 2 different scenarios: a non-Schwarzschild black hole and traversable wormhole geometry. So the first step of the code may run the code for the ray tracing, for the trajectory of light rays, depending on different values of the data. This is for Schwarzschild. So green for direct trajectories. A light ray was emitted here and come all this way, came to the server, which is located here. This orange is for photon, for lensing emission. For instance, this one crosses the quadrilateral plane once, a second, and then gets to the server. The red is for the photon ring. For instance, this one crosses the quadrilateral plane 1, 2, and 3 times. And every time a photon does this, picks additional luminosities. But at the same time, the range of input parameter values allowing you to pick additional luminosities is strongly diminished. And because of this, the exponential suppression of the luminosity. Okay. This black is what is the first image of the HD, what it was called the inner horizon. Because in this black actually it's not well written, so it's nearly here. Okay, so those light rays that do not cross the quadrilateral plane once, the only place they could have horizon is the even horizon. But because the even horizon, nothing can go out, so this is an utter blackness region. No light rays can arise from there. Okay, this is what you have here. This blackness region here is because those light rays have never intersected the quadrilateral plane where the disk is going to be located. So there is no possibility of any emission of light rays. So this has to be black. This is why this is the inner shadow. Note that in the intermediate region between the photon ring and inner shadow, no problem at all. Because if the disk is extended in this region, the inner edge of the disk is over here, can emit radiation that can come out of the object. Okay. So this explains this image. And if you allow this modification of the Schwarzschild solution to a black hole geometry of this kind, and you do the ray tracing, so you get this. As you can see, this is extremely similar. There are small differences in the width of the regions and so on, but not that much. Also, one things are different because there is no even horizon. Because of that, they have no inner saddle because light rays can come out, or because this is a two-way wormhole. The light rays can come out, being originated in on the other side of the wormhole. Right? So this is why this is in black and this is not. Okay. Now, this is the ray tracing. Second step, this info feeds the accretion disk program. You do this in order to construct your image, you get this thing. So this is for model 1, picking at the innermost stable circular orbit for time-like observers. This is the emit. This is the observer. It has two effects, gravitational resist, and then contributions for the different orbits, for the 3 times of emission. And this translates at 3 different peaks. You can see here. This is direct, this is lensed, and this is photon ray. As you can see, the direct emission is very large, has a very large region. The lensed is much is strongly diminished, and then the photon ray is almost a spike. And this is consistent with the idea that the contribution to the luminosity is going to be exponentially suppressed. When you demonstrate the image, all this thing is the direct emission. And then there is a ring here, plotted in red, and this is the lensing ring, which is this one. There is another one, which is not seen at first sight, but I can guarantee you that is there. If you make zoom in, which is inner to this thing and corresponds to this star. So as you can see, there are additional light rings beyond the direct emission. Actually, that's the main goal that you are pushing here, trying to split these light rings and wait for for an improvement in the sensibility of the detectors, in order to allow you to separate, to see whether in this image, as you can see here, whether there is actually an structure of sub-light rings being here. According to general relativity, it should be. But general relativity solutions give you extra predictions about the properties of the light rings. If these properties are different from what you would expect, that could be a signal of new physics. Because the luminosity depends on the accretion disk model, but the location of the rings do not. The location of the rings do depend only on the background geometry, not on the details of the accretion disk. The luminosity depends on the accretion disk, but not the position of the light rings. When you do the same exercise for the black bound geometries, so you get more or less the same, some tiny differences in the height and width of the peaks. The image is slightly different, but it's very difficult to distinguish from general relativity expectation according to making with the current observations that we have right now. You can go to model 2 and then do the same exercise. And what you have here in Schwarzschild is that there is an overlapping of emission. So somewhat the photon ring and the direct emission has been overlapped, and the lens as well. And instead of having the light rings clearly separated, like in this case, you can see they are overlapped. In such a case, you cannot resolve the individual light rings. What you can resolve is the luminosities. Whether the luminosities are different, actually they are different, these two models, but it's extremely difficult to distinguish with observations. Because as I said, the luminosity depends on the accretion disk. So even if you see a discrepancy in your model and the luminosity of the light rings in your model, it could be not related to the geometry, but to the accretion disk. So very difficult. If you go to the relevant for the HD observations, so it's the same problem. So this and this look extremely similar. Okay, so this is the main problem with this kind of idea. So either you look for an object where the accretion disk is far away from the horizon and then the light rays are clearly isolated, or you need to find something that allows you to discriminate between these two images. What is this something? So suppose that your compact object has more than one critical curve. Could this be? Nothing prevents your model from having this picture. So suppose that you have a model with two critical curves. For instance, this one, which is actually this is Bardeen solution. If you have played a bit with regular solution, a kind of extension of Bardeen solution to implement a wormhole nature at the center. You do the ray tracing again, and because there are two critical curves, one in yellow, another in red, so the spectrum of light trajectories is much more complicated, but can be also classified, just being a bit systematic. So I'm doing it for a particular set of values, and what you get is this was for the previous model, very similar, right? The images very similar among themselves. What happens in this case? So things change a lot. You can see here you have the direct emission here, another light ring, which is the lensing ring, another the photon ring now is more visible. It collects more luminosity, but there are two additional light rings. These two additional light rings are associated to the new critical Q that you have. And the image, as I said, is very different from what you have in this thing. So this thing and this thing now are very different. Right? And the same happens here. So it has to be compared with this one. You can see this one and this one are again very different. There is a new kind of light ring here with luminosities that is not in the other case. And when you go to the HD observations, I mean the model related to the HD observations, so you can see it's extremely different. Actually, it's too different in the sense that it's hardly viable as something to represent what the shadow in 87 galaxy, right? It's too extreme because we wanted it to be too extreme in order to clearly find some kind of image which is very different from the irregularity expectation. Now, this object, I'm using this kind of, I'm using a very toy model, right? But there are models which are not all models having more than one critical Q. Okay. As you can see, in this case, the shadow and the light rings are very different when you have modification of geometry that actually are not that drastic, right? So, because asymptotically, this is Schwarzschild. It's just when you get quite close to the center of the object when differences start to arise. But the image is completely different, right? Actually, you don't need to go to extreme modification of the Schwarzschild geometry. Even if you consider a regenerative black hole with a tiny amount of charge, there are strong differences in the location of the sub-light rings. The light emission is the same thing. So you cannot distinguish between a regenerative black hole and a Schwarzschild black hole by the light emission. But the properties of the sub-light rings, they are very different. So actually you can distinguish here. If you go to other modifications of the geometry like this one, so the shadow is very, very different. Right? Now, there are further models with more than one critical Q, right? One thing first is that the inner shadow only exists if the object is truly a black hole. If the object is not a black hole, if there is no even horizon, whether it's a wormhole or it's a boson star or whatever, then there is no inner shadow. There are always contributions at all values of the impact parameter, no matter the values. Again, the problem is computing the luminosity and finding something that you can observe, but there is no inner shadow. And there is another idea was recently built by some people working on the HC actually, on this idea of what they call an asymmetric wormhole. The wormholes, usually when you study them, they tend to be symmetric, they are simpler, they are easier to build, but there are also examples of asymmetric wormholes in the sense that it's not the same solution on both sides of the flow. In such a case, the effective potential on each side of the flow is not the same. And what happens here is that you have a region above one of the maximum, below one of the other, below the other, where a light ray, with these values of input parameter, goes this way, keep the potential on the other side and goes back. So in such a case, what you have? In this side, you have associated to this curve, the usual scatter of light rays that I was showing you. But those with these input parameter values, also associated to this maximum, produce a new set of light rays associated to light rays that came from this asymptotic infinity, closed the wormhole through, bounced back, and came back to infinity. So this is a historical representation. So this is not actual colors associated to models of luminosity. Actually, because it's quite more difficult to implement numerically this situation. So it can be that as well. Now, the efficiencies of this analysis. So assumptions that we are making. First of all, I suppress the rotation. No problem, because it is known that the contribution of the rotation, even in the maximal limit, is less than 7% of the shadow size. So quite small. You can neglect it of this approximation because there are other things that you don't know well. But and these things are related to here these things. It has answer on emissivity, associativity, intensities, and so on. This is model dependent. So you have a larger degeneracy here and here. As a first step, you can remove rotation because it quite complicates the finding of the light range. Not all these are optically thin. If it is optically thin, there is no new structure of light range, and this is a problem because that's where the finer details of the modifications to the geometry could be. Now, geometrically thin, probably they are not. They are not even spherical either, but something between. So intermediate shape that you need to integrate in your code in order to see more realistic images. Now, these images that I was showing you are taken head-on. So it's a black hole that is perfectly directed to you. Usually, this is not the case. Actually, in HT, this is 17 degrees. So you need to modify your code to make some inclination, and this changes a bit the shape of the light range and the luminosities. Actually, this is why, let's see here, so there is, let's see, there is not symmetric, the luminosity. Right? There is some change here because of this. Actually, this modify the luminosities of your model. Okay? And also slightly the position of the light range. And then, of course, these models are very toy models for geometry and for the emission these things that you can do in the future. So I was saying, because two black holes, transit versus radiant nostrils, can be extremely similar in direct emission, the same thing, but can be very different at the level of the surface. This is what happens with radiant nostrils. So if you have a collection of black holes, you can study the light range structure and start doing pseudography, right? Analysis of light range properties. Because why is this so interesting? Because the guys working on this field of very long baseline interference, they claim that in future aggregation of future observations, we are going to actually be able to detect the diffuse but very sharp contributions for the light range. But they are going to be able to measure this. So if there are new light ranges that are not expected in the Kerr solution, so it could be a signal of the existence of your favorite compound object. Because there are some people working in extensions of the Kerr black hole to, for instance, as Andrea was mentioned, discussing how solving the problem with the singularity. So you have singularity-free rotating black hole supported by reasonable matter sources. So then you can plug it into your favorite code and try to see what kind of light range it produces. So the testing of these alternatives to the Kerr hypothesis is already up. That's it. Thank you.
Thank you very much. I think there is a question in the chat. Victor Alfonso raised the hand. He wants to say something. Victor, can you hear us? I cannot hear him. Haroldo also raised the hand. Haroldo, can you hear us?
Yes, can you hear me?
Yes, you can ask.
Oh, so can I ask?
Sure, yes.
Okay. Thanks for the very nice presentation. It's a very interesting work. I would like to ask if you have some results for when the accretion disk is not geometrically thin, because there is a paper by Janssen where he obtains that Janssen et al., where he obtains that these sharp peaks on the observed intensity are a consequence of the geometrically thin assumption. So if you assume like a different geometrical distribution, you can have you lose this very thin signature. So have you investigated something in this direction?
Yeah, so it's two different things, right? So there are two hypotheses, one for the geometry of the disk and another one for the optical properties of the disk.
Yes.
Actually, removing the idea that the disk is optically thin is off of our interest because we are actually looking for the finer details in the structure of the light range. If the disk is optically thick, then such light ranges do not exist because those light trajectories, these light ranges are produced by light rays that are traveled several times around the black hole. If the disk is optically thick, then every such photon will be reabsorbed by the disk and will not produce any light rays. Now, the other hypothesis that this is geometrically thin, so this is not geometrically thin, that's for sure. So then you need to upgrade this scenario to take into account the thickness of the disk. That's something that we are very interested on doing it, because that's a more realistic situation in order to see how your light rings will be. So actually, among this pool of ideas, so considering the idea will be to include rotation, considering inclinations, and then generalize the geometry of the disk to be some intermediate shape between spherical and infinitesimally thin. The point is that if the image is spherical, sorry, if the disk is spherical, then there are new light rings. But these light rings are displaced up to the regular curve. So this will be the shadow will actually corresponds to the not to the inner shadow but to the regular shadow. I mean, it will fit the critical curve. So that's interesting as well. So in the intermediate state, so you will see a displacement of the position of the disk to the outer region, depending on how close the spherical is. And that's something that we would like to introduce in our analysis. But it's something we're working on that. Actually, I was more interested on finding new, qualitatively new features, as I was mentioning, this new structure of light rings. So, because it's where I think the better opportunities are in order to see whether there are new physics in the future. So in order to do that, so you need to complicate your background geometry. In such a case, there is also new troubles that arise with the code, right? So every new situation needs upgrades of the code continuously. So we are working one at a time in order to solve every problem. Right? So it's because of this slide of all the assumptions we are making. So every assumption that you remove, you need to make an upgrade of the code to deal with the new scenario. And it's not always easy, particularly for us that we are new arrivals to this field. But I think this is a very good opportunity, particularly for young researchers, because part of the future is gravitational waves, part of the future is shadows for those that work in gravitational phenomenology. Okay.
Okay, thank you.
Okay, so is there any other question here?
Yes. I understood that you were studying the light rings for the wormhole case.
Mm-hmm.
The light rings from the same side as from the same side of the wormhole as where the accretion disk is located.
Mm-hmm.
But what from the other side?
Yeah,
what if we are looking to a wormhole who doesn't has an accretion disk in our side, but in the other one?
So if you read this paper, this is exactly what we discussed.
Okay.
So we discussed three different scenarios. One is yours. We don't have results. This is something with a model. It's not published yet, but this is with all the calculations made. But then we have another two scenarios. One of them is the one you are mentioning, but we didn't implement it yet. Actually, that's something I'm doing because I'm very interested on doing that. What happens if the array was originated on the accretion disk on the other side? Particularly in those scenarios where the wormhole could be asymmetric, not be the same solution, right? Because the only light rays that can come to you in such a case, okay, this plot, light rays that come to you from the other side come in a very specific impact parameter region, okay? Because there have to be only those that exit from this maximum value of the impact parameter. So they arise in a region of the impact parameter value which is inaccessible to those light rays originated on your side. So there will be also a proof that there is something flowing from the inside of the horizon. Okay, so this the maximum is here, so there is a region between the photon sphere where light rays can come out. Okay, but once you determine for geometry there is a minimum value, which is the inner shadow. So in the So in the Schwarzer case, this is utter blackness. If you see light rays inside here, those light rays can only come out being oriented on the other side, not on your side, because of this.
And I guess the throat radius, the position of the throat will affect this.
Yeah. There is a connection between the impact parameter value and the radius of the throat, telling you where is the region where these light rays will come out. Problem with that is, in my case, is that the luminosity is going to be extremely low as compared to what you have.
Yeah.
So difficulty to detect it.
Because there is not this feedback.
Yeah, because they are going to turn several times on the tape around the going from the other side to the throat and exit to yours, and then they have to circulate again or to go back to yours.
Exactly.
They lose energy doing that, so they lose luminosity. But something we don't have a model telling you exactly how this works.
Okay, so I think we should move. Well, first of all, we should thank again Diego. And now we will move to the next speaker, which is Aroldo online. So maybe Florencia, are you there?
Yes.
Yeah, I'm here. Can you?
Yes. So let me.
Read
Presenter. Okay. Now you can share your screen.
Let me see here.
On the left bottom.
Can you see my screen?
No yet.
Not yet.
But you have. Okay, I think you appear here as presenting, but
yeah. So there is like a updated animation. Let me see here.
Okay. Yeah, you can upload your file or share the window directly. Okay, now.
So here it say that it's started. So can you see my screen?
Yes, I can.
Okay.
Yeah. Okay. Yes.
So everything's okay now, right?
Yes. Yes.
Okay. Okay. So let me start.
Yes.
So I will start by thanking the organizers for giving me the opportunity to present my work here in this very nice workshop. So my work is entitled Short Black Holes Immersed in Strong Magnetic Fields, Shadows and Lensing. It was written by me in collaboration with Pedro Cunha and Carlos Hedeiro from the University of Aveiro and Professor Luis Crispino, my advisor, at the Federal University of Pará in Brazil. This presentation is based on this Physical Review D, which is also available on this archive here. So this is the outline of my presentation. I'll give some motivations. After that, I will talk about the model, the toy model we study. And then I'm going to talk about the nude geodesics and the light rings, shadows and gravitational lensing. And after some final remarks. So as you may know, in the recent years, the collaboration Event Horizon Telescope imaged the first shadow of a compact object. And in order to compare the results obtained by the telescopes with the theoretical predictions, they used the general relativistic magnetohydrodynamics in order to obtain the simulations. And the consistent models are accretion disk with a non-negligible magnetic field. So here in this upper part, we have the results from 2019, as Diego explained. So we have here the signature from the accretion disk, and this bright, in the central dark region is somehow related to the shadow of the black hole. We have also this second result on this 2021, on this year, which is this image here, which is like the superposition of the intensity map with the lines of the electromagnetic field which surrounds this black hole. So it's like a signature of the magnetic field around this central black hole in the M87 galaxy. So these general relativistic magnetohydrodynamics are very computationally expensive simulations. And one can ask if you can obtain analytical solutions of Einstein field equations that models black holes immersed in external strong magnetic fields in order to get some analytical insights in this black hole surrounded by external magnetic fields. So these solutions, do they exist, or in analytical form, do we have a simple toy model? So the answer is yes. We have this magnetized Schwarzschild solution. So it's possible to obtain this magnetized Schwarzschild solution, which is basically a Schwarzschild solution immersed in an external constant magnetic field through this so-called Harrison transformation. So you basically take this Schwarzschild solution, you apply this Harrison transformation, and at the end you have the Schwarzschild solution immersed in an external magnetic field. Of course, this superposition of the black hole and the magnetic field is not linear. You have no linear effects. And the line element is given by this expression 1 here. So it has this lambda here, which is related to the external magnetic field. So B here is the magnetic field strength. And now you may notice that this solution here is static and axially symmetric. So it's a little bit different from the Schwarzschild, because Schwarzschild is static and spherically symmetric, while this is static and has an axis of symmetry, which is related to which is the direction of the external magnetic field. So this Harrison transformation you can apply to other solutions, for instance, the Heisenauer solution, the Kerr solutions, and this is already known. But we explored the shadows and the gravitational lensing for the simpler solution, which is the Schwarzschild magnetized one. So this geometry, so the price you pay for adding this external magnetic field is that the geometry is not asymptotically flat, because the magnetic field is constant, so it goes constant up to the spatial infinity. So even at the spatial infinity, you have the influence of the magnetic field. And you may notice that this line element 1 here possesses a horizon. We do not call it an event horizon, because an event horizon is a global concept. Instead, we call it an apparent horizon, which is a local concept. You can always find, for instance, in simulations of binaries, they use most of the concept of apparent horizons instead of event horizons, because it's a local concept. So we can show that R equals to 2m is an apparent horizon by analyzing the expansion of the null geodesic congruences. So here, theta L is the expansion of the outgoing, and theta N is the expansion of the ingoing null congruences. And at R equals to 2m, the outgoing becomes 0, and this side R equals to 2m, it is negative. So, which is the condition for an apparent horizon. The surface area of this apparent horizon is 4 pi r squared, where RH is 2m. So the radius and the area of this apparent horizon is exactly the same of the Schwarzschild one, but due to the axial symmetry, the geometry is not exactly the same. So here in this figure, we show the embedding of the apparent horizon in a Euclidean 3 space for this magnetized Schwarzschild solution with different values of B. And you can notice that the the geometry of the apparent horizon becomes prolate as we increase the value of B. Now, in order to study the no geodesics and the light rings, we use the Hamilton's equation described by equation 6 and 7, where the Hamiltonian is given by this equation 8 here. And since the metric components of this short magnetized black hole do not depend on T and phi, we have these two conservative quantities, 9 and 10 here. So in general, in an asymptotically flat spacetime, this E is the energy as measured by an observer at spatial infinity. But since now we have this persistence of the magnetic field at the spatial infinity, this will not be the case. So this E here is the energy as measured by an observer at infinity at the x of symmetry, only in this case. So the interpretation of this constant is a little bit different here. We can split this Hamiltonian as a kinetic term and a potential term. Here T is the kinetic term and V is the potential term. So this potential term V here depends on the two constants, E and L. And we can define a new effective potential, which is this H here, which does not depend on the constants of motion, depends only on R and theta. And so we can study several analytical aspects of no geodesics using this effective potential H. For instance, if we take theta equals to pi over 2, we analyze the equatorial plane case, which is not the general case since the geometry is not spherically symmetric. But for the equatorial plane, we have this behavior here of the effective potential. So we have a maximum value here and we have a minimum value. So we may have two light rings, and which one is stable and the other one is unstable. So moreover, we can show that the new geodesics in this magnetized threshold black hole it obeys this following inequality here. So where this eta is the impact parameter, is the ratio between L and E. And geodesics will propagate whenever this one of the impact parameter is greater than the effective potential. And the equality holds at the turning points. So when B is different than 0, as R goes to infinity, this effective potential H goes to infinity. And this means that a generic light ray can only escape to infinity if at eta equals to 0, which means that it can only escape to infinity if it's moving radially outwards the black hole. So these results are mainly due to the external magnetic fields. And we can also study the light rings in this geometry, which are determined by equation 16 and 17. And from equation 17, we find that at the equatorial plane, the light rings are located as this, as given by this equation 18 here, which is a cubic equation. And using the Descartes rules of sign, we can see that we can check that this cubic equation here have 0 real and positive solutions, or 2 real and positive solutions for R and different values of B. By solving this equation numerically here, we can indeed confirm that there exists a critical value, which called BC, this critical magnetic field, such that for B less than this critical value, there are two light rings outside the apparent horizon, one unstable and the other one is stable. And we call this on the critical magnetized threshold black hole. But for B greater than this critical value, there are no light rings outside the apparent horizon. And we call this over critical magnetized threshold black hole. And this is somehow a novel result, an intriguing result, because usually when you have a black hole, you have at least one unstable light ring outside the horizon. And this is guaranteed by a theorem published by Pedro Cunha and Carlos Herrero. And the thing that is happening here is that this external magnetic field is modifying the asymptotic behavior, and then you modify this theorem proven by Pedro and Herrero, and you open the possibility for black holes without any light ring outside the apparent horizon. The exact value of this critical magnetic field here is given by this expression here, which is approximately 0.19. So now we can study some properties of the shadows and the gravitational lensing of this magnetized Schwarzschild black hole. In order to do that, we use the backwards ray tracing method, which consists in involving the light rays from the observer position backwards in time until the light ray is captured by the black hole event horizon or is scattered to a sphere of finite radius. So in order to do that, we solve these two equations here for t dot and phi dot. Together with the equations for the r and theta coordinates, 22 and 23, which comes from the geodesic equation. And in order to solve this set of differential equations, we need to supply initial conditions. So these initial conditions, they are obtained by computing the form momentum of the photon as measured by a static observer. And the tetrad basis of this static observer in the magnetized Schwarzschild black hole is given by this expression 24 to 27. And here this zero vector, this E0 vector is the forward velocity of the observer, and the other three vectors are the spatial directions of the observer. Then we can obtain the components of the form momentum of the photon measured in the static frame by projecting the form momentum, P mu, in the tetrad basis. And the result is given by these four expressions here, 28 to 31. And then we can adopt two celestial coordinates, which are the angle along the equatorial plane and the angle in the theta directions, given here by beta and alpha, respectively. And we can write the three momentum of the photon in terms of these two angles, as given by 32 to 34. So using these three expressions here with these previous results, we can obtain the initial conditions computed at the position of the observer for different values of alpha and beta. So so the procedure here is to adopt a given angle of alpha and beta, and then we evolve we obtain the initial conditions given by 35 to 38, and then we evolve the geodesic equation and check if the light ray falls into the event horizon or escape to infinity. With this, repeating this procedure to several values of alpha and beta, we can obtain a map in a beta alpha plane with a color map in the alpha beta plane. So this color map depends on the type of pattern you choose for the celestial sphere. Here we choose this pattern of the celestial sphere divided in four different colors, red, green, white, and yellow. So here we put the observer here denoted by this person with hands up. Then we have in the forward direction, we have this bright spot on the celestial sphere. We have here the back of the observer. We have the north and the south, the east and the west. If you do this procedure to a flat spacetime, for instance, Minkowski, we end up with this result here. So the front is the front with the bright spot is located here. And you have here the back of the observer, which is now which now split in 2 points. The north and the south, becomes this line here, this upper line and this bottom line, because we are mapping the coordinate the points of a sphere into a plane in order to obtain an image. So this is a property of the mapping. In the following, so before presenting the ray tracing results, I remarked that two observers will be said to be under comparable condition if the perimeter radius, which is defined like this, so it's the square root of g5 phi computed at theta equals pi over 2. The perimeter radius is the same in both cases. So if they have the same perimeter radius, which is an invariant measure of distance, they will be said to be under comparable conditions. This perimeter radius is not equal to the radial coordinate, and it has a dependence here on B. So first, exploring the shadow and gravitational lens results for the uncritical case, which is most likely to model astrophysical cases where the magnetic field is small, this value of B is small. We have these following results here. First, we have the Schwarzschild result, then we have these three different results for different B's. B equals 0.03, 0.04, and 0.05. So first, for the Schwarzschild result, we have this result here, which is very common in the literature of shadows and backwards ray tracing. We have the four different colors on the celestial sphere. Here, the bright spot behind the black hole appears as this bright ring here in the observer plane. And this bright ring is called the Einstein ring. It's related to the fact that all the rays with this given impact parameter here hits the point behind the black hole. Inside inside this Einstein ring, we have an inversed image of the celestial sphere, and this is related to angles that are scattered with an angle greater than pi. And next to the shadow edge, we have the celestial sphere with the normal orientation. And in fact, if we zoom in next to the shadow edge, we have this alternating behavior repeating infinitely in a fractal way. So now for B equals to 0.03, we have this result here. So we already notice some difference in the scattering. For instance, the Einstein ring is not so evident. And then, in fact, as we increase the value of B, the Einstein ring disappears. For instance, for B equals to 0.04, we have two bright points here, one in the top, one in the bottom, one in the left, one in the right. And this is related to the loss of the spherical symmetry when we put the external magnetic field in the Schwarzschild black hole. And we also notice that the shadow edge becomes oblate as we increase the magnetic field in the uncritical case. So despite this magnetized Schwarzschild solution being not asymptotically flat, it can model the near horizon geometry of a black hole immersed in a strong magnetic field. So now we consider the overcritical case, which is considering large magnetic fields, which are not likely to be the astrophysical case, but we can push this limit, this theoretical value, and see what new features happens in the shadow edge. So in this case, since we don't have light rings at the equatorial plane, we can ask what determines the edge of the black hole shadow on the equatorial plane in this overcritical case. So here I show the backwards ray tracing results for an overcritical magnetized Schwarzschild black hole, and we have a very distinct features in comparison with the undercritical case. So here I choose a BM equals 0.02. The observer is along the equatorial plane and in this perimeter radius here. So first we notice that the shadow and the scattering are chaotic, which means that for very similar initial conditions, the point that the light rays hit the celestial sphere can be very different. And in order to study some in detail some features of this result, this backwards ray tracing result, we took 3 different points here, 1, 2, and 3. And we tried to see what happens to the path of the light rays as it evolves in time. So here in the left, I show the contour plots of the effective potential. The black regions are regions forbidden for the photon to cross. And in the right panel, I show the path of the photon, the path that the photon traces at the time it evolves. So here the blue is the observer position and the black is the position of the celestial sphere where it hits the celestial sphere. So we notice that due to the external magnetic field, the strong magnetic field, the photon traces a very complicated path before being scattered to the celestial sphere. And if we take a similar, very close initial conditions, this point here can be very different. So now for the point 2, we have this point that falls into the event horizon, which gives this shadow here in this region. And again, we see that the photon traces a very complicated path before falling to the event horizon. And for the point 3, this path is even more complicated. So this chaotic region, arises due to this complicated path that the photon traces. Now, we notice other feature. So when there are no light rings along the equatorial plane, it's just a shadow. So we call this panoramic images because the observer will see along the equatorial plane just a shadow. 360 degrees is just shadow. But outside the equatorial plane, we have a well-defined boundary of the shadow. So one can ask what defines this boundary of the shadow outside the equatorial plane. Because, for instance, in the spherical symmetric case, the light rings, they determine all the points of the shadow edge. And here, in this static axially symmetric case, the light rings determine only the shadow along the equatorial plane. So what we obtained is that this shadow edge outside the equatorial plane are determined by fundamental photon orbits, which are more generalizations of light rings, and which are these closed orbits that can span some theta, maximal theta angle. So my final remarks, so we have studied the shadows and the gravitational lens in a short-wave black hole immersed in an external magnetic field. For high values of the magnetic field, the black hole solution presents no light ring at all outside the horizon. While for small values of the magnetic field, it can have one unstable and one stable light ring. Performing backwards ray tracing techniques, we were able to show that for small values of the magnetic field, the shadow becomes oblate, but it's somehow qualitatively similar to the Schwarzschild shadow. I recall that these small values of the magnetic fields are the most are the ones close to the astrophysical case. For high values of the magnetic fields, there are these panoramic shadows due to the absence of the light rings. So along the equatorial plane, the observer sees only shadows. And for outside the equatorial plane, there are these fundamental photon orbits, which determine the shadow, the shadow points outside the equatorial plane. So I end my presentation here. Thank you very much.
Thanks, Geraldo. Really nice presentation. I don't know if there are questions. Sergi, the audience.
Other questions here in the audience? Comments? No? Anything online before I start speaking? Questions? No? Okay, so I have some questions. By the way, very nice talk. I'm sorry for being a bit late, but I was teaching at this time. I missed the first part, so maybe you have already explained this. So, can you justify the motivations, the physical motivations to consider these magnetic fields?
Yes, let me back to the previous slide. Okay. So here, in the HT results, they compare the results obtained by the telescope with this general relativistic magnetohydrodynamics, and the consistent models, the models that fits the obtained results are accretion disk with non-negligible magnetic fields. And in fact, this is the 2019 result, which is only the intensity map of the accretion disk and the black hole. And we have also this new result, the 2021, this year, which they obtained the intensity result of the black hole and the accretion disk, and these lines of electromagnetic fields surround the black hole. So they have, I think they put some estimations on the electromagnetic fields that is around this central black hole. So this image here is a superposition of the intensity map and the lines of the field of the electromagnetic field. So these lines here, which looks like some hairs, are the superposition of the intensity map and the lines of the electromagnetic fields. So we asked if we can obtain some toy model to analyze these black holes immersed in external magnetic fields. And in fact, we can do this, which is this magnetized Schwarzschild solution obtained by this Harrison transformation here, which is basically a transformation that you take a Schwarzschild solution, and at the end of the transformation, we have the Schwarzschild solution immersed in an external magnetic field. You can do this with all the geometries, for instance, Heisenostro and Kerr.
Okay, and
yes, we have...
Yes, I have more questions.
Sorry.
Yes. So in this case, in the case of M87, the magnetic field would be generated by the accretion disk, right?
Yes.
Okay. And is it reasonable to assume that it is actually symmetric, or is just an approximation? Well, it's a reasonable approximation, I guess.
Yeah. So they obtained a result for a poloidal magnetic field. And here the magnetic field is a little bit different because, so this is a toy model. So in this case, in this analytical solution, the magnetic field is is axially symmetric, and it's constant given by this field strength here.
Okay, and one other question. So you were showing the image generated by the event horizon team, which is using as the source, the light source, an accretion disk. But in your calculation, you use this pattern with colors. So,
yes.
Can you change your pattern of colors with an accretion disk to generate something like this picture?
Yes, so we can do something like this. But we haven't done yet. So we just took this more common more common illumination pattern, which is this celestial sphere illuminating the black hole from all the directions. But we can also improve these models, this light source model, by considering an accretion disk in the equatorial plane of this geometry, and this accretion disk has some emission profile. This is some perspective for this work.
And in your opinion, what is more difficult, to use this pattern or the accretion disk? What takes more time in order to analyze the geodesics and all that? It takes time to find the direct emission. So,
yeah, so this pattern here, we only have to, this pattern of the celestial sphere, we only have to deal with the path of the node geodesics. If you were to consider an accretion disk, we would have also to solve the radiative transfer equation. I think that for this under critical case, it would not be so difficult to do this, because the motion of the light rays are regular, they are not chaotic. Here, this case, I mean. So we can solve the geodesic equation coupled with the radiative transfer equation. In this case, it would not be so different of the Schwarzschild case. But for the chaotic case, it can be somehow tricky, because, well, I don't know if it's well known when you solve the radiative transfer equation when you have chaotic behavior.
I see. And so on this last picture that you are showing now, how did you do the calculation? Using Mathematica, Python?
So in this one here, we used C++. We also confirm some of our result with using Python, using a different code of Python. But Python takes more time to evolve this result here. This one here, where we could compare with the Python, with this one here, with the Python and or C++ code that we developed, because the light rays are not chaotic. But here, this one here, we have some difficulties, and we could do only using the C++, which is faster, because the light rays can trace very complicated paths like this one here, and this takes time. And C++ is faster, so.
I see. And when you say faster, what is the time scale? Just to have an idea.
It depends on the quality of the image. For instance, this one here, I think, well, 20 minutes, 25 minutes.
Okay.
The other ones, which are more regular, it takes like 10 minutes with a good quality.
I see. Very good. I'm very impressed. Okay, I have, from my side, I'm very satisfied with your answers. I don't know if Dino wants to say something, because his hand is raised. Please. I don't know how long.
Yes, just to complement what Haroldo already answered, but maybe since you have lost the beginning, just to make some points clear that Haroldo made it along his talk. But I mean, your questions have been very interesting, and it's good also to wrap up by saying that in this model, we are not considering an accretion disk, right? That is, I mean, as Haroldo said, in the perspectives, that's exactly one of the projects Haroldo is touching upon now. But just to make clear that all these results are not, we are not considering accretion disk. So it's very difficult or impossible to compare with the AHT images themselves in first place. And the second thing is that this image that is being shown now, that Haroldo is showing now, is for a very, I would say, not astrophysical situation, because a very, very high magnetic field. So we don't expect, I mean, to see something like that in nature. I mean, it will be very interesting, but we don't expect. It's the images more compatible to astrophysical situations are those images. We have some effects already. I mean, the Einstein ring being split in Einstein points, and as Haroldo has mentioned, right? And one last thing that I would like to add is that when Haroldo says 25 minutes, when Haroldo says 10 minutes, he's speaking about unusual computer, his personal computer, right, Haroldo? This is a good thing to make the point to the audience, because sometimes you just have to use a cluster or something like that. There are clusters available, but these things are performed in unusual PC, Haroldo's PC, to be more precise.
Yes.
That's okay. So thank you very much for your questions, Gonzalo, and thank you.
Thanks a lot. I'm very impressed. I've been playing recently with the version Beast and ray tracing and all that, but I never imagined to be able to do to map a pattern like yours with that precision. It's really nice. I want to learn all that.
Thank you very much.
I'm looking forward to seeing you in the lab.
Okay.
Thanks a lot. Okay, so let's thank Haroldo again. And I think we are done with the morning session. Okay. So let's thank you. Who is the next one?
So, Mauricio, are you there?
Yes. Can you hear me?
Yes. Can you share your screen? I think.
I hope so.
Okay, now you.
You are now presenter, Fabrizio.
Okay, thanks. I see I can. Ooh. What should I do?
On the left button, you have a plus.
Yeah, share external screen.
Yes, you can choose to upload the file or simply choose the window to share.
Okay, I'm trying. Let me. But no, sorry. I have to upload the file. Can I upload the PPT file? It's working with that?
I think so, yes.
Okay. But it's not letting me share the screen, I guess.
Okay.
So I'm loading it up.
Okay.
Okay.
Yes, now.
Yeah. Okay. So let me. Okay. Okay, so you can see it, right? Because I see also the cursor, but I see it small. So okay.
You can put it bigger in your own.
Yeah, I found it up.
Screen,
Thanks.
just to be
But then
more comfortable.
Okay.
Okay.
So let me. I think I can start now.
Yeah.
So this talk will be mostly an overview of what we expect to be possible to be done with black hole shadow in the future. So you know very well, and the talk before me showed that the AHT has opened this new avenue for the study of gravity, but black hole shadow can be important also for cosmology. And I will try to, let's say, convince you that there's some real problem to overcome at the moment, but to be competitive with other kind of observable that can trace the cosmological evolution, basically the distance redshift relation. And I will try to compare them with other observable that trace the same stuff, the same kind of distance in the universe. So let me start with an overview of why we need this kind of observations. The main problem that we have in cosmology is that the Planck mission has confirmed the validity of the lambda CDM model with a precedent accuracy. Oh, I think my conversion went wrong, so you cannot see the number here, I guess. So let me see if I can. You cannot see the number, right? Because I don't see it. Let me see if I can do another kind of sharing. Oh, probably this is better. So now you can see my screen, right?
Just a minute.
Much better, right? So you can see the presentation here. Yeah. Okay, so now the number are there. Sorry. So basically, what I was saying is that the Planck mission has confirmed the lambda CDM paradigm with a precedent accuracy, but it's also raised some very strong questions, let's say. So the main, here I summarize some of them, which are the more prominent at the moment, and with cosmologists that try to give an answer with different model, with different possibilities and stuff. And I think probably the main problem at the moment is it's the so-called Hubble tension of discrepancy, which arises between measuring the Hubble constant between early and late time universe, and the tension is now just recently the supernova people that measured this with the Cepheid star. I will give you more details later about this, perhaps. Have raised this, so I've reached the comparable accuracy with the Planck mission, and have led to basically to this tension giving a 5 sigma statistical significance. So at the moment we think this is new physics, but we don't have a clue about what it can be. And also, like, there are other problem with the Planck lensing that is still probably related to late time physics, because the Planck lensing likely trace basically the evolution of the universe and not just the recombination physics. And also the so-called curvature anomaly, which is somehow related to the Planck lensing stuff, and both of them are not in agreement with the standard cosmological model at more than one standard deviation, and these are raised some question about some systematic in Planck, or the possibility that that there is new physics that is not being considered here. So there is also discrepancy still between lensing, basically in the dark matter clustering, between the weak lensing experiment, which are still late time experiment, and the Planck constraint on the same quantity. And what still remain open is the physical nature of the dark energy and inflation, which related to all of this. So in principle, all of this may be related. Even generally, they are thinking to be they be thought to be separated and be dependent on different things. But I like to think, this is just my opinion, that they are all related somehow, and that measuring the value of the Hubble constant can in principle shed light on all the other problems. There are also many more that I'm not discussing here because are not related to what I want to say later, but this is just a small overview. And the idea is that whatever you're considering, so if it's Planck or other, this is a plot that shows the tension between late time measurement using supernova calibrated in different way with respect to Planck and non-Planck experiment that uses late time observable to measure the Hubble constant. And you see that the tension is basically going at least down to 3 sigma, which is still high in terms of statistical significance. But you can raise at 6 sigma if we consider a particular combination of data. For example, Planck, it's always more than 5 sigma tension with late time data. So you can also remove, the important thing is that you can also remove Planck from the picture and use the Big Bang nucleosynthesis and the BAO oscillation, the baryon acoustic oscillation to do the same things. And basically this is very well in agreement with Planck, even though the statistical significance is much lower. It's always but you still see that there is a strong tension even if you remove Planck. So we think at the moment that the CMB is not the only observable that has a problem with late time. So it's more like early versus late time universe. So to understand why we need new observable, I want to take a small, this is very naive in general, but to what it is the Hubble constant, because it is really related to the foundation of the theory, not just, it's not just connected to the expansion. And the reason is that basically, if you take a dynamical point of view, so here I'm using FRW, but this can be extended to more complicated kind of expansion. The idea is that H naught is the value of the expansion rate that you get from the Einstein equation, assuming a perfect fluid, and that you know the matter energy content. So in principle, you say that H naught is the velocity of an observer at the current time. And this kind of extrapolation of the value of H naught depends on the assumed cosmological model. But you can take a more geometrical point of view and say that the Hubble constant is not just the velocity, but is also a way of scale of putting an absolute scale to the distances in cosmology. And this will not be a problem in the analytical representation. If not, we need to measure this. And when we measure this, we have a problem in measuring distance in cosmology. And the reason is that we don't know the absolute calibration of this, which is given, of course, by H naught. And when we look at what we use as observable in cosmology, they're the so-called standardizable observable. Here I made a collection. You see that each of them depend on some quantity that we don't know how to measure or how to fix by the theory itself. So for example, in standard scenario, you have the so-called shear mass redshift. So the amplitude of the strain of this gravitational wave is given by the radio of this and the distance. So you only know the distance or if you have any information about the mass. So you can measure the mass so the problem here arises, for example, that arises here is that you don't know the redshift because you don't know the redshift of the mass, but only the mass in the local frame. But you can measure the L, but then you cannot associate it to a precise redshift. So this creates a problem reconstructing the distance redshift relation. More common standard observable are the so-called standard ruler and candles that basically uses the idea that you can measure the acoustic oscillation of the primordial plasma, and you can trace their evolution by knowing this air, that this R here connected to the recombination physics. Or, for example, the supernovae that need an absolute calibration of the magnitude because you only measure the relative magnitude is mx of z. So the idea is that, oh, I jumped one. So the idea is that H naught is not only connected to how we measure things, but also to what we see in the sky. So let's take a look more specifically at one of these standard observable, which are the BAO. You can see where the problem arises here, because for measuring, so the BAO are an excess of probability, basically, at a fixed distance from a central galaxy. So you can do a galactic, you can measure your galactic field, and then pointing on one big galaxy, you can measure the correlation function of this galaxy, how it scale with the distance to the central galaxy. And what was found, this is the first paper that found it, is that there is a bump in the 2-point correlation function of the galaxy that corresponds to the distance that a sound wave has traveled between redshift 0 and the recombination, between the start, well, until recombination. So the idea is that if you know this RS, you can auto-calibrate the BAO, because you can measure the angular size of them in the sky by just measuring this galactic correlation function. And there is also, but the problem is that RS will depend on the sound speed, the sound speed, and this is a function of the cosmological model. So in the end, you cannot measure this RS. What you can do indeed, it's you can remove the dependency from the absolute scale by just using the fact that if you have many of these BAO along the line of sight, then you have access to this combination, the combination of h of z and rs. So you can measure the expansion and you can create this constraint basically. But you see that you are basically lowering your constraining power because of two constraints, you get only one at the end. And they are also degenerate with one another. So this is just a recap of what I said in the previous two slides. So in the end, you see, you want to know H naught, and this is the culprit of two things: the calibration of your observable and the calibration of the theory in a sense. So if you know the theory, you can go back, measure H naught, and then know the calibration. But if you know the calibration, you can measure H naught and go back to the theory and measure some quantities that are important for the theory. For example, the cosmological model, or measuring nearby distances, or the age of the universe. So all of these are interconnected, and we need somehow a way to disentangle them. So what we are trying to show is that, so this is a paper that we just released in collaboration with other, with Natalie Hogg and William Jarret. We basically assume that, so we basically tried to use all late time observable. Here we combine standard ruler, candles, and clocks and assume that the distances are related by the usual distance duality relation. And we try to measure H naught by using this combination of data set, assuming that you only can have small deviation from the DDR. What we found is that, so here you can see the plot, the triangular plot, the blue curves is the combination of data set using only late time data set, and the other two curves represent the combination of our data set with two prior, one from Planck and one from on H0, one from Planck and one from the supernovae result. And as you can see, what we found is that there is a discrepancy in the measure of the DDR that may between our result and the Schu's result that may indicate that there is a tension in the description of the propagation of massless particles. So the idea is that all of the things I showed you before, so the calibration and how this is related to H0 and the cosmological model, depends on how massless particle photons propagate toward us. So it could be that these indicate that there is some breakdown of the propagation of photon towards us. So now how black hole shadow enter the picture? Well, they are basically like BAO, because we can measure the amplitude, the angular size of the shadow, and then we can treat them as a typical standard ruler. So, so basically knowing the actual size of the shadow, the physical size of the shadow, which is fixed by the theory, we can measure in principle dA. The fact that they're like BAO, it's actually only in the expression that you give to the amplitude of the shadow, because if you remember, I show you that the BAO depends on the cosmological model by the definition of the sound speed that can change a lot in different cosmological models. But here, instead, we have the mass that calibrates the distances. So provided that you can resolve these black holes and measure the mass, then you, with multiple observation of the same astrophysical object, you can derive the distance and measure the redshift, the distance redshift relation, because also the redshift is accessible through photometry of the black hole. So this is what it's possible to. This has already been proposed to use them as a standard ruler, but there are some problems. So what we know is how to parameterize the size of the shadow in a simple black hole, so in a simple space-time. This is the original paper from the 66 from Singe, where this was calculated the first. And as you can see, the idea is basically that photon can escape, but this escape, not all of them can escape. So it basically calculated what he called the escape cone of these photons, and this is the original formula for a Schwarzschild black hole. So this is very useful in principle, but in the end, a detailed calculation is needed to assess if this can be extended to a cosmological scenario. So why? Because basically there is a transition between what we see in the vicinity of the black hole and what we are in the universe, in a sense. So basically what we calculate for this shadow is it's the shadow as seen by a static observer that it's static in the black hole and in the black hole system of coordinates. So it's not a time-dependent solution. So what we need is to connect it with an observer that instead is co-moving with the space with the expansion. And typically this is what we do. So we expect that that very long distance, the static coordinate in the spatial space-time will turn into the non-static coordinate of distances in the FRAW metric. The idea is that this is being calculated in a given metric where the spatial black hole can be connected to the FRAW metric, which is called the McVitie metric. And basically they calculated the overlap, which is this. But this work only, so for what I know at least, this work only for a black hole, for a spatial black hole that is immersed in an expansion. But it's very complicated to know what happens if you slightly change the spatial solution. So for example, if you have a charged black hole or other kind of exotic stuff, and even if this is rotating, then the extension is not so easy. So in principle, more calculation are needed, and this talk is also to point out this problem that if we don't know the correct way of parameterizing it, then we cannot reach the precision that we have for the BAO. Because of the BAO physics, we basically know much more than what we know about the physics of this object. But there are interesting avenues for them, and the reason is that being dependent, so if you assume that it's a spatial black hole, so it's not rotating, and then we can use the McVitie metric to extend it to a co-moving observer. Basically, what we found is that this is the scaling at fixed max in redshift for one of these spatial black hole, and you can see these two dashed line, the dashed and the dot line. The dashed line is the current sensitivity of the AHT, and this is what is expected to reach in few years, let's say. And as you can see, there are two regions. So this is due to the fact that dA, the angular distance that appear in the definition of the shadow for the co-moving observer, it actually increase until a center point, and then it starts to decrease. So these allow to have black holes that are invisible in a certain redshift range, but then they become visible at very high redshift. So in principle, this can allow to measure not only local like H naught locally, but also to measure a redshift range which is inaccessible with other observation that we have now. The only one that is planned for the moment is to use the so-called SKA observer to measure with the 21 centimeter emission to map the same redshift. So probably in the near future we'll have also the SKA observer measuring this. But the black hole are very promising in this sense. So just to recap, I want here so let's compare them. So at the state of the art, the BAO are very good to measure the cosmological model, because the main feature is that the physics is well understood, and basically they can be treated as in linear perturbation theory for all the history. But they have the problem that the absolute calibration can be only determined if you know something about the cosmological model and the recombination physics. But also you can imagine that they are basically unfeasible to measure past redshift 2 or 3, because the 2D correlation function is just don't have information about this, because the overdensity is not formed before that over that redshift. In turn, the black hole shadow have an evolution, so they can map at an higher redshift. So probably they can arrive at redshift 10, which is quite good for mapping age of the universe that we don't know anything about. And the BH must be determined independently, but it's also an advantage of this, because you can also test your mass model compared to the shadow. However, there is a problem to use them at the redshift equal 10, and it's that the evolution in time of their mass is dictated by accretion and basically also plasma physics. So, and possibly there is also merger coming in. Basically, this will be a late time, but we still expect that the merger will play a role. So we don't know. At the moment we don't know enough because there is no agreement on how they evolve. We don't know enough to be precise enough to predict something with the same precision that we use for the BAO. But the physics of the BH is well understood locally in the end, so we expect that this can be extended in the near future. So in principle, you cannot do a lot with them for the moment. So it's the idea of this breakup is that it's very futuristic to expect that they will possibly map Z equal 10 in the near future, because also the HT is planning to have an upgrade, of course, but they're basically dedicating much of their time to measure close enough black hole that can be treated not in the Hubble flow, basically. So for the moment, this is a bit futuristic, but it's a promising avenue and possibly will be competitive with other observations like SCA. And so my last part is about what you can do with them in the closed universe. So I show you that you can measure H0 with them in principle. So what you can do, it's using them to calibrate the supernovae. So I don't know if you're familiar with supernovae, but basically the idea is that supernovae, as I was saying, can trace the evolution of the cosmological model by measuring the difference in their absolute magnitude with respect to the magnitude measured at cosmological redshift. And the idea is that this allows you to access the distance luminosity. However, there is a problem, so that they need to be calibrated because M cannot be measured. We don't know what's the absolute magnitude of this supernovae. And so typically they are connected with the local universe using a distance ladder, which is basically only a way of interpolating the distances of this supernovae in the Hubble flow back to the local universe. So typically this is done in 3 rungs, as you can see here. The first is our local universe, so the Milky Way and some nearby galaxy. And then the intermediate rung, it's a way, it's a point where you need a Cepheid and a supernova in the same point, in the same host, and this allows you to use Cepheids to calibrate the supernovae, and then also the Cepheid are not absolute calibrated, so you just connect them to the Cepheid you see in the local universe, and you can measure with parallaxes and other stuff. And knowing how they evolve in redshift and how their period luminosity change, you can basically trace this line and measure the distance to supernovae. However, you can substitute this with the black holes, because as I show you, if you know the mass of the black holes, basically the black holes give you a distance luminosity, and they basically are expected to appear in every galaxy. So in principle, a supernova will always have a supermassive black hole counterpart in their host. So the idea is that they are very abundant, and also they are expected we expected to be seen in the vicinity of our so basically in our local universe most of all. And what we are trying to do is to predict what will be the outcome of using them with certain assumptions. So this is very preliminary. We still need to include a lot of systematics here, but if one can reach 10% error on the shadow sides, and assuming the mass error, it's going to be subdominant, which is mostly the case for M87. You can see that here with just 5 of this shadow, we can reach twice, so basically a sensitivity which is 10%, but it's very promising in terms of using them for the distance ladder and to measure H0 in the local universe, provided that you can reach this 10% error. And we also here we are using basically what we know now about the AHT, but in the future maybe we can improve more. So this is very promising in terms of realizing a distance ladder that doesn't need a local anchoring, and that they can be absolutely calibrated with the mass of the black holes. So to conclude, I show you that BH shadow offer a powerful way to test both strong gravity regime and the cosmological model, but they may reach redshift not accessible with current cosmological probe, shedding light possibly on many open questions in cosmology. And the problem, however, still lies in the theory of embedding the Berkeley in expanding universe, which is poorly understood, and also as well as their evolution through time. So basically, these are some of the questions that will need to be addressed in the future to make accurate precision of the size of the shadow, but also of how it's seen by the co-moving observer. And also, I mean, I'm not considering it here because I'm not an expert of this, but there are many problems with plasma physics, which some have been addressed by the collaboration, the AHT, but some are still to be addressed, as we also see so in the previous talks. And it is very promising. So in conclusion, this is very promising, but there's still some question open to reach the accuracy that we require for measuring cosmology with standard ruler like the BAO or the CMB. Oh, and with this, that's it. Oh.
Thank you. Really nice talk.
Sorry, I see myself twice.
Who's speaking? Okay, is there any question here in the audience? Okay, Fabio, you can go ahead.
Fabrizio, can you hear me?
Yeah.
Okay, so your talk was about standard rulers, but I wanted to ask you something about standard science. That in one slide at the beginning, you were saying that GWs could act as standard science. No? You can take back, yes. Yes.
Yeah, no? Yeah, this thing.
On the top, yeah, okay. So you said that it's not easy to use that as standard science because you have some kind of degeneracy between measures and theoretical predictions, no? You can obtain the same results by changing the cosmology parameters and or the theory, no?
Yeah, sure, yeah. Basically, you don't know the mass in the system of reference of the binary. So you don't know the redshifted mass. You know only the mass in your reference frame. So you cannot predict the redshift.
Yes, this is, I think that this is true if you look at a purely gravitational signal. I wanted to know if you know if a possible multi-messenger detection could remove this degeneracy.
Oh, sure, yeah. A separate observation that can give you the missing quantity that you need, then you have an absolute calibration. For gravitational wave, of course, GRB, so the counterpart, the optical counterpart would be the way in which you can infer the redshift, right? But the problem with this is, so there are two problems that I see with this, which could prevent them to be abundant in a sense. One is that the GRB that it is produced sometimes in this binary, it's not very well understood, but for sure it has to be highly collimated in one direction along the binary angular momentum, no? So in this case, you need to be very lucky that the GRB is pointing toward you, otherwise you lose it. So you may have the gravitational wave, but not the GRB, right? So this is a first problem. And the second is that we cannot predict, at least now, how many of these binary will have a counterpart. So the question remains open, of course, but I see them. So let's say that when the first counterpart was found, they were, so the gravitational wave people were very happy about the fact that it would be abundant and stuff, but then we didn't see any other counterparts, so they may be that there is one over 10 years or something like that. So the number of counterparts is still a debate on how much they are. But if I have so my opinion is that there will not be that abundant. So maybe we will not have a lot of bright siren.
Okay. And I have another question.
Okay, a short one because
from the previous talk, we have seen that magnetic field can distort the shape of the shadow. So I think in your work you didn't take into account this effect, but I think that you should include it, no?
Sure. The problem here is, I think this can answer your question. The problem is that this connection that we have done, it's based on the fact that you assume a sparse black hole. So this metric that is being used for connecting the moving and the static observer lies on the fact that you assume a sparse black hole. So with a sparse black hole it's doable, but I don't know if you can do the same kind. So basically what you need to find is the right metric that can do the local to non-local transition, basically, you know? So this is the problem. So all these effects that you are seeing must be included. And for example, the rotation also has a strong, well, not strong, but strong in the sense of the accuracy we want to reach. So for example, not knowing the spin of the black hole will cause a 5% decrease in accuracy. So like a 5% indetermination. So this is already too much for cosmology, you know. So all these effects must be accounted, and we have to find a precise way to measure the shadow side. So yeah, all these effects must be accounted for thoroughly.
Thank you.
So let's thank again Fabrizio.
Bye bye.
We'll meet again at 3 p.m. Okay? So see you then.
No queremos llegar a hacer sí, es uno de no, entonces pues estuvo de
Hello everyone, we are back, but we have problems with the camera here. Vale.
Okay, no problem.
Just give us a second. No, I think yo creo que es esta, ¿no? Ya, sí. Ahí no. Okay, we are back. No, the camera doesn't want to work. Anyway, since the talks now are online, we don't need the camera here. So I'm not going to spend more time with this. So Param, are you there?
Yes, Gonzalo, I'm here.
Okay,
Can you
very
hear
good.
me?
Yes, I can hear you clearly.
Okay.
So Andreu, cuando puedas poner aquí para que nos vean por aquí, ya está.
I'm not sure how to start the.
No, I have to. Okay, you can see the screen now. You are present. You should have 4 buttons at the bottom, and one of them is the camera. Is the button to share your screen.
Okay, just 1 second. Can you see me also?
Yes, now we can. You look great. Very.
Okay, let me just see where the screen is. 1 second. Okay, can you see the screen?
Yes.
Okay. So let me start quickly. So thank you so much, everyone. Like, it's very nice to participate again in this workshop. I'm sorry, like, I'm not able to attend all the talks because of the time difference, and also it's the end of the semester. So I'm going to talk today about some recent result which I have obtained with my postdoc Bofi Lee, and it's available in this paper, which is on arXiv. And essentially the result questions a very common wisdoms in classical cosmology and various modified theories of gravity, which states that if you have a negative potential, let us say a negative cosmological constant or an aprotic potential, then we know that with a negative cosmological constant in cosmology, it's very easy to get a recollapse of. If there is a recollapse, then in classical cosmology, it is followed by a big crunch. If you have a quantum theory of gravity which can resolve the problem of big crunch, then there will be probably a bounce, and therefore there can be cycles of bounce and recollapse, bounce and recollapse, and so on. So in this paper, we actually found that one of the very prominent modifications which comes from loop quantum gravity in loop quantum cosmology completely rules out any viability of cyclic models. In other words, if these results hold, then if cyclic models are true, then a very prominent version of loop quantum cosmology will be ruled out immediately. You don't have to look at any other observational data, and vice versa. If it turns out that a particular version from loop quantum gravity of modified theory of gravity is correct for whatever other reasons, then our universe cannot have a cyclic history. So this is the main message of the talk, and I will try to go slowly in some parts, but I don't have probably much time. So Gonzalo, if you can kindly give me like 5 minutes heads up before the talk ends, I'll be very grateful.
Okay, I will do.
Okay, so we all know that inflation is a popular candidate for describing the physics of early universe, but it is past incomplete, essentially proven by the theorem by Bode, Guth, and Vilenkin in 98, which essentially states that even if you have inflation, but if you evolve the universe backwards from inflation, there will be a Big Bang singularity. Inflation has also been criticized various times because of its lack of naturalness. What is inflaton? What are its initial conditions, and so on. And recently, there have been various attempts from the Swampland conjecture by various people and the Transplanckian conjecture by various people like Brandenburger, Steinhardt, and Waffa, which question that whether the inflationary models which we use, whether they are Starobinsky inflation or chaotic inflation or whatever, are they even consistent with the expectations which we have from effective field theories derived from string theory? So there are, even though inflation is quite popular, there are still some fundamental issues. Therefore, there have been always some sort of alternatives which have been promoted for inflation. These include bouncing models in which there is just a single bounce, like the matter bounce scenarios, or cyclic models such as the aprioric cyclic models, in which the universe goes through various phases of cycles of contraction and expansion. Now, these models also have their own problems, but the proponents of these models, they claim that they can be distinct signatures. But the main problem from the quantum gravity viewpoint for both inflation and these cyclic models is the existence of Big Bang and Big Crunch singularities. Even in the aprioric cyclic models of Steinhardt and Turok, these singularities are just resolved in a very ad hoc way, and many times they are just assumed, they don't exist. So quantum gravity effects are expected to resolve the Big Bang singularity and leading to non-singular inflationary and cyclic models. And it turns out that if you look at the quantum gravity effects even in the non-singular inflationary models, then there is a possibility of models where inflation is preceded by a cyclic phase, such as in spatially closed models. And we know, like some of the recent CMB data, it favors slightly spatially closed models, depends on which data one looks at and what one excludes. But there has been a problem which has been pointed out by Linde from last 20 years, and this is the problem I discussed in the previous winter workshop here, that if you have a spatially closed model, then inflation is very hard to start for energy inflationary models which are favored, like Starobinsky inflation. And there I had discussed that if you have loop quantum gravity effects, then it becomes much, much easier. But then there are some cycles which happen before inflation, and then inflation proceeds. So the point is that cyclic models are not just exclusive. Cyclic evolution is not just exclusive to cyclic models. It's quite possible that the pre-inflationary branch, even if one is a believer in inflationary paradigm, it's quite possible that our universe went through some cycles, small cycles, before inflation actually happened. Okay, so the main point is, if quantum gravitational effects are important and very important to complete these inflationary and cyclic models, an important question is whether any of these paradigms, inflationary and cyclic models, can be ruled out by quantum gravity. Now, in this talk, I will be just focusing on the cyclic models. But this is the main question which we want to answer, that if inflation and cyclic models, they are going to be completed only by quantum gravity, we should be asking, are there any constraints from quantum gravity which affect the viability of inflationary and cyclic models? And my goal will be to show that one prominent quantization from loop quantum gravity just completely rules out any viable cyclic evolution. Okay, so let me just give a brief introduction. In the last 15 years, like loop quantum cosmology, which I will denote by LQC, which is based on techniques of loop quantum gravity, has provided useful insights on singularity resolution and its phenomenology. Various results have been obtained by groups all over the world. The main result is that the Big Bang or Big Crunch singularity is resolved and replaced by a bounce. When coupled with an inflationary potential, quantum gravity effects result in inflation as an attractor for isotropic as well as an isotropic spacetime, which means that if you have an inflationary potential given, then after the bounce, inflation turns out to be an attractor, and the probability of inflation turns out to be extremely high. So inflation is naturally embedded in LQC. Similarly, quantum gravity effects have been also used to understand problems with aperiodic models, and it turns out that loop quantum cosmology effects can alleviate various problems of the aperiodic and cyclic potential. So loop quantum cosmology has been successfully married both to inflationary models as well as the cyclic models. But the standard loop cosmology, which one is generally familiar with, which has been quite active from last 15 years, is based on various simplifying assumptions, and it's in fact only a simplest possibility for quantizing cosmological spacetimes based on loop quantum gravity. Like in any quantum theory of gravity or any quantum theory, there are various ambiguities which we have to understand, and these ambiguities become important in loop quantization, and we have to understand the robustness of physics akin to these quantizations. So as an example, there are different regularizations of the Hamiltonian constraint, and I will come to that, what it means. And different regularizations, they lead to different versions of loop quantum cosmology. The question is, the basic question is, are inflationary and cyclic models compatible with these regularizations? Now, in the last 2 years, there has been a lot of work on understanding these regularizations and whether they are compatible with inflationary spacetimes. And there have been results in cosmic microwave background, for example, which have been understood at LSU by Ivan and by me and by Baufi and so on. And these results tend to agree that there are subtle differences. And so far, the wisdom has been that yes, there are different regularizations. Yes, there is a change in Planck scale physics, but that change in Planck scale physics is just confined to the Planckian regime when it does not translate to any striking differences later on. And I would show that that is not the case. So the main result of this talk, because some parts may be unfortunately somewhat technical, so I don't want that anyone misses the main punchline. The main result of this talk is that assuming validity of effective dynamics, which I will come to what it means, which means that assuming that there is an effective description, we show that one of the main versions of loop quantum cosmology, which is what is this Thiemann regularized loop quantum cosmology, which is much better motivated, which is the modern version, which probably has better link to loop quantum gravity, it rules out possibility of any cyclic evolution of our universe resulting in a classical regime. What it means is that if this version is true, then our universe could not have gone through any cyclic evolution, which resulted in a classical spacetime. If Thiemann regularized LQC, which is also known as MLQC1, M for modified LQC version 1. So sometimes I will use Thiemann regularized, sometimes I'll use MLQC1. They are both synonymous to each other. Is correct, then our universe never went through any cyclic evolution. So this is the outline of my talk. First, I will discuss briefly about GR and cyclic models, showing that how cyclic models are so easy to obtain. The standard LQC, I will give a very brief introduction just for some students who may not be aware of various results in LQC. I will be just talking about dynamics here. There have been plenty of results on perturbations by Ashtaker, by Ivan, and by Gupt, which I will not be able to point out. Then I will come to Thiemann regularized LQC, which is a modified version of standard LQC. Then I will discuss modified Friedman dynamics from GR and the prospects of cyclic evolution. And then I will give examples. First, a very simple cyclic evolution, which can be generated from a negative cosmological constant, and then aperiodic potential. And these examples will show, both in the presence of a scalar field and in just with a negative cosmological constant, what actually happens. And then I will just summarize with open issues. Okay, so let us come to GR and cyclic evolution. So just we are doing standard GRs. The Friedman and Raychaudhuri equations are given here. Hubble square, which is h square, is 8 pi g by 3 rho, which is the energy density of matter fields. And a double dot by a equals minus 4 pi g by 3 rho plus 3p. This is the Raychaudhuri equation. The conservation law, rho dot plus 3h rho plus p equal to 0, where capital P is the pressure. When you integrate it, it gives you rho proportional to a to the power minus 3 1 plus w. I'm assuming in here that the equation of state is fixed. This equation of state w is p by rho. Now, if let us say if you have a dust dominated universe, then w is 0 because it's rho goes as a to the power minus 3. This universe goes through decelerated expansion. If one adds a negative cosmological constant or a negative potential to the matter density with w greater than minus 1 by 3. So let us take a dust-filled universe. Then w is 0. So w is greater than minus 1 by 3. W greater than minus 1 by 3 is important because it tells that the strong energy condition is satisfied, which means from the Raychaudhuri equation up here that the gravity is attractive. So in this particular case, it's easier to see that if you have dust-filled universe or radiation-filled universe, if you just add a negative cosmological constant, which will amount to adding a term like rho minus rho by rho lambda, where rho lambda is lambda by 8 pi g, with lambda negative here, that is why there is a minus sign here, then it's easy to see that future evolution, this rho and this rho lambda will balance out each other. They will cancel each other. The Hubble rate will vanish. And when the Hubble rate will vanish, this will cause a recollapse of the universe. And this recollapse of the universe will cause, so if suppose you start with a dust-filled universe, forget about the Big Bang, maybe quantum gravity will come and resolve it. If you have a radiation and dust-filled universe, the universe is expanding. If you put a negative lambda, at some point in future evolution, this negative lambda will balance the expansion, will make the Hubble rate 0, and the universe will then head towards a small scale factors, which will lead to a big crunch singularity. Then the cyclic model, if you want to construct, essentially requires that you should just have a means to resolve the big crunch singularity. If you can resolve the big crunch singularity and you can have bounds, then there will be a bounce, and then the cycle will again start, and so on. So cyclic model is pretty easy to construct in this way, and that is essentially the game which is played in various cyclic cosmologies. Add a negative potential, make some assumptions about singularity resolution, and will keep on going on, so on and so forth. And this is the conventional wisdom. You can search the literature. This is the conventional wisdom. Essentially, the idea is consider a negative potential, or which is like cosmological constant or aperiodic potential, to cause a recollapse. If quantum gravity effects resolve the singularity, a non-singular cyclic model is guaranteed. So this is essentially the punchline of various models. But I would now show that there is a counter example, which is what we prove in this paper. That counter example means that yes, you can have such a scenario. In fact, like the quantum gravity model, which resolves all the singularities, it is completely non-singular. Yet, even if you add a negative potential, it won't lead to cyclic model. So this might look very surprising why it will happen, but let us see why it will happen. So a very brief introduction to loop quantum cosmology, just to fix the ideas. Loop quantum cosmology is based on techniques of loop quantum gravity. It's a canonical quantization of symmetry-reduced spacetimes, which uses Ashtegar-Barbero variables. And these are the connection A's and the triads E's. And the quantization is based on holonomies of the connection and the fluxes of the triad. So essentially, this is like the gauge theory of gravity using Ashtegar-Barbero variables. The key result of loop quantum gravity is that the geometry at the quantum level is discrete. It's not an assumption. It comes from the theory, and the space-time is atomized. The discreteness of geometry translates to an upper bound on the space-time curvature, and the differential geometry of GR is now replaced by quantum geometry, and therefore the dynamics is not governed by differential equations, but the dynamics is governed by a non-singular difference equation. The loop quantum cosmology started by seminal work by Boyewald in like 99 to 2001 and so on, but it was given a rigorous footing by Sticker, Boyewald, and Lewandowski. And one of the first consistent models was formulated by these people in 2006, in which they figured out the quantum gravitational Schrodinger equation for a spatially flat isotropic model with a massless scalar field. And the left-hand side, the G mu side, essentially translates to this part, which tells that this is a difference equation with volume V of the universe, and phi is a massless scalar field which acts as time. And this is the right-hand side, the T mu part of the Schrodinger equation. What happens is that at volumes much greater than the Planck volume, this difference equation becomes the Wheeler-DeWitt differential equation. And we know that the Wheeler-DeWitt theory essentially agrees with GR, and this implies that when the gravity becomes much weaker at volumes greater than the Planck volume, then Einstein's theory is recovered. So this is just a standard plot of where I'm plotting the wave function of the universe with volume and phi. So you start from a very large, you take a sharply peaked state at very large volume and phi, and you evolve this state backwards towards the Big Bang. Then the state bounces to another branch of the universe, from the expanding branch to the contracting branch as you move backward here in time. So this is the red dots here show the expectation values of the volume computed versus phi. And these match very nicely with the classical GR, this is the expanding branch, the blue curve, top blue curve. As you go back, it goes to a Big Bang. Then there is another branch, which you start from a contracting branch, and if you move forward, it goes to a big crunch. What LQC does is to join these two curves, and it leads to a bounce at the maximum density, which is 0.41 rho Planck. This is completely fixed by the parameters in the theory. There is no freedom here. The nice thing is that this singularity resolution is achieved without any violation of weak energy condition, which is generally the case. Like if you look at various models, people violate weak energy condition to resolve the singularity. There is no violation of weak energy condition at all in this singularity resolution. There is no fine tuning of any parameters. There is no fine tuning of the initial conditions. You take generic states and they will bounce. And there are a lot of work which on this, even using supercomputers. Classical Friedman dynamics. This is a standard LQC is recovered here. You can see that the blue curve matches the red curve very quickly as soon as the density of the universe decreases below 0.1, and it also is recovered here. And the nice thing is that for suitably chosen coherent states, there is an effective dynamics and effective space-time descriptions, which captures the entire evolution, which you can actually write. The point is you can write a modification of a Friedman equation whose solution actually completely matches with this red curve. Okay, so now let me come to the theme and regularization in loop quantum cosmology. The reason why this regularization appears is that the Hamiltonian constraint, on which the loop quantum cosmology is based, it can be quantized in different ways, resulting in potentially different physics. Basically, it is composed of the Euclidean term and the Lorentzian term, where the Euclidean term is given by this expression and the Lorentzian term is given by this expression. F is the field strength of the connection, E's are the triads, and this is the determinant Q is of the spatial metric. Similarly, K's are the extrinsic curvature components. We don't have to go into the details of this, but the main point is that in spatially flat models, like the K equal to 0 isotropic homogeneous spacetime, like a very important caveat, like I'm sorry if I didn't said that loop quantum cosmology is a quantization of homogeneous spacetime. So this is we are considering isotropic and homogeneous spacetime throughout. So in the spatially flat models, you can combine these two terms before quantization. So because of symmetry reduction of the isotropy and homogeneity, these two terms can be combined before you quantize. Is a simplification which occurs. And the standard loop quantum cosmology is based on this particular simplification. If these terms are treated distinctly, they are treated differently, as will be the procedure in full loop quantum gravity, then the form of the quantum Hamiltonian constraint will be significant. It turns out to be significantly different. So the one significant difference is that this difference equation I showed you, which was a second order difference equation, it actually becomes a fourth order difference equation. This leads to what is called as a Thiemann regularized loop quantum cosmology, or what is also called as MLQC1. So the main point is that there is a gravitational constraint, Hamiltonian constraint, terms, the Euclidean and the Lorentzian terms. In symmetry reduction for spatially flat models, you can simplify these two terms, massage them, join them together before quantization. If you do that and then quantize, then it results in standard loop quantum cosmology. If you don't do that, if you quantize them before you do anything with them, then it leads to Thiemann regularized loop quantum cosmology. Now, the second strategy is what one will do generally in loop quantum gravity and in more general scenarios. So it's not that it can be taken lightly. So what is the effective dynamics of the second one? It leads to this particular effective Hamiltonian, where V is the volume of the universe equals A cube. Lambda is related to the smallest area of loop quantum gravity. And then it leads to this particular effective Hamiltonian. This is the gravitational part, and this is the matter part. B here is actually just is equal to the classical Hubble rate in the classical theory, but B is the is related to the extrinsic curvature of the spacetime. So if you solve this, then which means that solve this putting it equal to 0, the vanishing of this effective Hamiltonian constraint, then it leads to sine square lambda with two roots, B plus and B minus, and it changes the maximum energy density. I'm calling it rho C1 because rho C was in standard LQC, and it turns out to be lower than the maximum energy density of LQC, turns out to be 0.097 rho Planck. So unlike standard LQC, the effective dynamics is composed of two branches for entire evolution. There is a B minus branch, which is the post-bounce branch, and B plus branch, which is the pre-bounce branch. And the modified Friedmann dynamics is far more complex than loop quantum cosmology. Let me show you how. So for the B minus branch, the post-bounce branch, the Friedmann equation is given by this equation. We can see that the first term, 8 pi g rho by 3, is the classical term. The second term, 1 minus rho by rho C1, is what is like the LQC. And then the new terms are these red terms in the bracket. For the B plus branch, the pre-bounce branch, even the first term is modified. It still looks like the classical term, but it has some beta in it, which depends on the Barbero emergency parameter gamma here. And a rho lambda emerges. There is an emergent cosmological constant, which is 0.03 rho Planckian, which actually emerges in this first term. This is a completely quantum geometric effect. Then this LQC piece, 1 minus rho by rho C1, and then this whole red piece, which is there. So if you look at the B minus branch, there is a GR term, there is a LQC term, which is here, and then there is this MLQC1 term. And the B plus branch is completely different from the B minus branch. It's very quantum because it has this first term, which is Planckian by itself. Then it has this LQC kind of a term, 1 minus rho by rho C1, and then this is the MLQC1 term. Now, in the asymptotic pre-bounce regime, if you go far before the bounce, there is still a bounce in this theory, but the bounce is very asymmetric in this case. In the far time before the bounce, then the Hubble rate just approaches this particular value where the Newton's constant is rescaled, and even though it mimics the Friedmann equation, the space-time curvature is almost Planckian because rho lambda takes an almost Planckian value. So the universe enters a pre-bounce regime, which is asymptotically de Sitter with a Planckian cosmological constant. Another interesting thing, which was not noticed till recently, is that in the B minus branch, which is the post-bounce branch, the minimum energy density is 0, as in LQC and as in GR. We know that in GR, the minimum energy density is 0, unless you put some field, which violates weak energy condition, and similarly in LQC. But in the B plus branch, even if you don't put any field which violates weak energy condition, the quantum geometric effects make the rho minimum not 0, but rho minimum is minus 0.023. It's quite large in the Planck units. So it makes a rho minimum which is very small. So both the B minus branch and B plus branch have a different rho minimum. So rho minimum is 0 as in LQC and GR. So therefore in the post bounce branch, the things would look similar to LQC, but the pre-bounce branch is quite different from what is GR and what is LQC. So let me now come to cyclic evolution, the prospects of cyclic evolution. And here I'm plotting the sine lambda B, which comes from the holonomy of the connection, versus B, which is like the connection divided by the triad. So B has to be thought of like a Hubble rate in the classical theory. This B is rho by rho C. This is 1 at the bounce, and this is 0 at the recollapse and in the asymptotic classical regime. This is the prospect of cyclic evolution in loop quantum cosmology. So I'm just plotting like what will look like the LQC curve. So P is a point which we can think of as a present moment. And let us say in this present moment, we have found that there is some negative cosmological constant. We are just trying to construct cyclic models. So let us not worry about the observational viability of this assumption. The bounce points are D and J, which is where this Z becomes equal to 1. The recollapse points are A, G, and M, which is where Z will become 0 because rho will cancel rho lambda. In the presence of a negative potential, starting from the point P in the forward evolution, which is given by this arrow, universe can reach G, which is where the recollapse will occur. And then it goes into a contracting phase towards a big crunch. That big crunch is avoided, and there is a bounce at J. And then the universe starts expanding again and reaches another point of recollapse at M. And then this branch here actually continues into this point A, and then there is a cycle, like a sinusoidal curve, which tends to infinity. So in loop quantum cosmology, since the pre-bounce and post-bounce phases both agree with classical GR is recovered, and we know in classical GR, it's very easy to construct a cyclic model where singularity is resolved. So loop quantum cosmology easily results in an infinite cyclic evolution. And this is shown also with the evolution of energy density. Again, starting from the point P, if you go forward in evolution, then at point G, there is a recollapse where the energy density would be cancelled. And then you move forward, there will be a big crunch towards a big crunch at J. Big crunch is resolved at the maximum energy density. Then the universe starts expanding, goes towards M, then it continues, recollapses at A or M, and then it goes again towards a D and so on. So again, there is a cyclic evolution. And I will illustrate this in further plots. So the Hubble rate vanishes when the energy density becomes 0 at the recollapse points. Important to note is that energy density is never becoming 0 anywhere. Therefore, there is no violation of weak energy condition. Singularity is resolved purely because of quantum gravity effects. Now let us see the situation in MLQC1, or the Thiemann regularized LQC. And as I said, it's more complicated. So this plot also becomes more complicated. So it looks like a similar situation, but the first thing is that there are these purple lines, purple horizontal lines here. This is where between them is a B minus evolution. And apart from there, between the purple and the red lines, there is a B plus evolution. The bounce points are B, F, H, and L. These are the bounce points. Why? Because this is where the Z is 1. So this is where the energy density takes a maximum value. The recollapse points are various here. So these are A, G, and M, which is where the Z becomes 0, like in LQC. But Z also becomes 0 at E, at for example, Z also becomes, the quantum recollapse also occurs at here, at J, and at D. So remember, like Z becomes 0 at E and C, but the quantum recollapse is a recollapse which occurs at rho minimum. So this is where D and J, there is a rho minimum. Okay. So the bounce points are here, BF, HL, but unlike LQC, there are two types of recollapse points. Unlike LQC and unlike GR, there is a classical recollapse at rho equal to 0, and there is a quantum recollapse at rho equal to minus 0.023 in the B plus branch, and these two recollapses occur at D and J. Now, for a cyclic evolution, if the cyclic evolution has to happen, then starting from the present, it has to go till M, then it reaches A, then these cycles have to continue and so on. But the universe must pass through now both the classical recollapse points, which is G, but also the quantum recollapse point, which is J, and then M, and A, and D, and G, and so on. So it's much more complicated. It has to pass through both classical recollapse point and the quantum recollapse point. Now, passing through quantum recollapse point means that suddenly the rho is going to become negative, which means immediately, first of all, that the weak energy condition is going to be violated, which is the first main difference between LQC and Thiemann regularized LQC. So let us look at the plot of the energy density. So if you plot energy density, then starting from the point P, which is the present moment, if you go forward, there will be a recollapse at G, which will be a classical recollapse. The universe is expanding. Recollapse occurred by negative lambda. Then it will reach a big crunch towards H, which will be resolved. But then the next recollapse, which will occur, will be not at I, but at J, which is what will be the rho minimum. It has to pass through this J, and then it goes through this L, and so on. So starting from P in the forward evolution in the B minus branch, universe can reach G, and then enters into a contracting phase between G and H. Then it changes the branch. It changes to B plus branch and reaches asymptotic de Sitter at I. At I, this is asymptotic de Sitter. It does not turn out to be the bounce. And only when the negative potential has magnitude greater than rho minimum, minus 0.23, it reaches J, which is the quantum recollapse, and that is where the weak energy condition is violated. So the main thing which we saw is that somehow, if you want to have a cyclic evolution in this Thiemann regularized LQC, you have to reach these points J and D. And that requires, since the kinetic energy of the field is positive, it requires that the negative potential must have magnitude greater than rho minimum minus 0.23. It should be more negative than minus 0. It should be 0.023. More negative and more negative than that. So that is a highly Planckian magnitude. Okay. So for lambda equals minus 0.01, let us take this example. It's a very large lambda, negative cosmological constant, but we are taking it minus 0.01. This implies rho lambda is minus 4 as 10 to the power minus 4. This is greater than the rho minimum, which is minus 0.23. The LQC universe undergoes cyclic evolution, but there are no cycles in MLQC1. So this is just an example that if you don't take a potential which is very negative, extremely negative in the Planckian, there will be no cycles. So this is the LQC universe. Red line, it goes through cycles. But if you look at the MLQC universe, there are no cycles. Two bounces here in the middle, and in the forward evolution, it reaches an emergent de Sitter phase, and the negative backward evolution, it reaches an emergent de Sitter phase. It never cycles at all. Similarly, again with this negative lambda, the universe in MLQC1 undergoes a classical recollapse. If you look at the plot of the energy density at G, it undergoes a classical recollapse at G. It avoids the big crunch and big bang singularities at F and H. In asymptotic past and in asymptotic future, it reaches a de Sitter phase with an almost Planckian curvature. The classical phase in MLQC1, which is this phase, is only transitory. It's not a permanent phase. On the other hand, in LQC, it goes through various energy peaks of energy densities and its valleys, and it keeps on oscillating again and again. We can also look at the equation of state plot here. I'm plotting here W inverse, and one can see here that the equation of state becomes quite negative in the case of the MLQC1, so the weak energy condition is violated. So the main point is that so far it was thought that even though we have different regularizations, the differences are only in the pre-bounce regime, but the post-bounce regime turns out to be identical. So this plot clearly shows, this plot and the previous plot clearly show that it depends on the matter content. If you take a negative cosmological constant, the LQC universe will keep on cycle. The Thiemann regularized LQC is not going to cycle. It's going to start from an almost de Sitter phase, and it's going to end in an almost de Sitter phase. It does not cycle at all. But certainly, as I said, like if only when the negative potential has magnitude greater than this, then it reaches quantum recollapse and there can be cycles and WC weak energy condition is violated. So let us see what happens if you take a very large negative potential, almost Planckian negative potential. So in this case, okay, so in this case, sorry, so this is rho lambda is minus 0.03. This should be 0.023. Yeah, again, I'm writing 0.23. For a rho lambda, which is extremely negative, the quantum recollapse does become possible, and MLQC1, the Thiemann regularized LQC, undergoes a cyclic evolution. And here I'm showing that if you plot V versus phi for this particular rho lambda, which is extremely negative, almost Planckian, then there are cycles which are present, and you can see these cycles are not symmetric because A, G, and M are classical recollapse points, and these are D and J are quantum recollapse points. And you can see from the equation of state plot, which is the W inverse here, that here W inverse is lying between 0 and minus 0.6, which means W is far more negative than 1. So weak energy condition is violated. So since I do not have much time, I won't be able to go through cyclic potentials, but the situation remains the same. If you take an aprotic potential, then MLQC1 does not give you cycles. It starts from asymptotic de Sitter regime. It leads to some sort of a small kind of a, and then it goes to asymptotic de Sitter regime. But on the other hand, the LQC curve, the red curve, it cycles. Same thing with, like, if you take an extremely negative potential, then again, like there will be some cycles and the clusters of bounces and so on. But the energy density, as we can see, remains very Planckian. It starts from 0, it goes to 0.1. It keeps on remaining in a Planckian regime without any classical phase. Same as here, that even though the universe becomes very large here, the energy density remains pretty Planckian. Okay, so let me just summarize. So the main point is that in classical GR, a cyclic universe is guaranteed to be obtained with a negative potential if the Big Bang Big Crunch singularities are resolved. The example is standard loop quantum cosmology itself. It resolves these singularities, the Big Bang and Big Crunch singularities, and can result in a cyclic evolution very easily, as I showed in the plots. The main point is this a genuine feature of loop quantum gravity? Do different regularizations of the Hamiltonian constraint yield similar results? Or does the nature of singularity resolution what's the viability of cyclic evolution? So essentially, we want to understand the robustness of the physics, which is coming from loop quantum cosmology, because loop quantum cosmology so far has been based on various simplifying assumptions. So far, it was believed that differences between different regularizations of loop quantum cosmology are small and hidden, either in the bounce phase or they are inaccessible because they are in the pre-bounce regime. In the pre-bounce regime, MLQC1 or Thiemann regular LQC leads to emergent de Sitter phase, but well, who can access that phase? One cannot go back. Even in the CMB, we cannot access really that phase. So it was believed that, well, everything is fine because in the post-bounce phase, these phases agree with each other. What we have shown is that this is no longer true, especially when different matter choices are considered. Unlike standard loop quantum cosmology, the Thiemann regularized loop quantum cosmology has two types of recollapses in classical and quantum regimes. Universe must violate weak energy condition at the quantum recollapse and have rho lambda greater than 0.03, which is an extremely large value, essentially completely makes unviable every cyclic model to allow a cyclic evolution. And this has no classically allowed regime. The lesson is that some quantization ambiguities may lead to striking phenomenological differences, making them falsifiable. In the sense that if we find a signature of any cyclic evolution in CMB, then Thiemann regularization will be completely ruled out. One cannot tune any parameters to save it. And the open question is incompatibility with cyclic evolution, which we have seen, is it a more generic feature of loop quantum gravity? There is some evidence that it is yes, from Kantowski's X models and so on. But I would say, like, we need some more work in this direction. Okay, I think I will stop here. I'm sorry if I have taken slightly more time.
Thank you. Thanks a lot. Time for questions, comments.
Albert, yeah. Any question on the chat? No? Well, you can take your time. Or Valencia, maybe you have something? No?
No.
So then, so Param, I have a question. Maybe you can comment on this. So is this incompatibility with the cyclic evolution, or these effects, that this asymmetry between the different branches somehow defining an arrow of time? Because you're breaking the right-left evolution. So is there a way to trace the origin? How do you explain the origin of this asymmetry in the time evolution, even more in this scenario where the time evolution is dictated by some reference field? So how can you comment something on that? Because I'm trying to understand the underlying reasons for this asymmetry, the lack of sight.
I think I think the question of the arrow of time is slightly complex, and I think generally we assume that there is some sort of a symmetric evolution, but and then we say like somehow the entropy decreases as we entropy increases as you are approaching bounds, and then it has to reset and so on. I think like I would personally say that we should not relate whether the evolution is cyclic or whether the evolution is symmetric or not with this particular evolution of this type with particular some sort of arrow of time. This asymmetry is arising just because of some quantum gravitational effects. This is a more generic feature than what we have seen in standard loop quantum cosmology. I would say, like, personally, I feel that the symmetric cycles which we have seen in standard loop quantum cosmology is really an artifact of simplifying assumptions. In more general scenarios, it appears to me from the loop quantum gravity that we will have a very asymmetric evolution which will rule out such cycles. But the question of how it leads to arrow of time is complicated in particularly in this case, because we have really an asymptotically de Sitter phase on one side and not a very standard phase on the other side. So I really don't have the answer to that question. I'm sorry.
Okay, thanks for your comment.
Here, another, sorry to interrupt you.
Marian.
Yes, Marian, would you like to ask by yourself, or I can read it? Okay, okay. So she's asking if are your results based on the fact that rho can reach negative values?
Yes, that the point is my results are based on assuming the validity of the effective space-time description, this effective Hamiltonian which I wrote here. These effective space-time description, and if you assume this effective dynamics, then the conclusion from the Friedman dynamics is that the rho minimum must reach negative values. Now that's a very good question. It may be that when we really derive this effective dynamics, maybe quantum gravity effects rule out this negative value. But if you assume the validated effective dynamics, then there is no way that this value would not exist. It would exist. So I'm not assuming any matter. This is just the vacuum, quantum gravity vacuum effect. Like in the quantum field theory, we have Casimir effect and so on, which leads to these negative energy densities. Similarly here, it's a purely quantum gravitational effect, which leads to this rho minimum, which takes this negative value. So I'm not assuming any matter which takes this negative value. It's a pure quantum gravitational effect, which manifests itself as an effective energy density, which does this.
Okay, thanks.
Any other question? You then? No? If not, so thank you so much again for your time and your nice talk.
Thank you.
Okay, thank you, Gonzalo. Thank you.
So now our next speaker is, so Adrián, take care of the session now.
Yes.
Or Florencia, you can.
Yes, I
yeah.
make him a presenter. So can you?
Yeah, Mary, my apologies, but I have to go to pick up my kids from school.
So, okay, so our next speaker is, with pleasure, Yarley Lobo, from Universidade Federada Paraíba. And he will talk about interference effects and the modified Born rule in the presence of torsion. So, Yarley, whenever you feel like starting, it's okay.
Okay, so can you hear me?
Yes.
Yes?
Yes.
Okay, and I think you can see my screen. So let's go. This is it. Okay. So you are seeing my screen correctly, right? In full screen.
Yes.
Okay. So, well, first of all, I'd like to thank Gonzalo and the other organizers of this very nice workshop. It's a pleasure to be here again. And I mean, as Adria already said, I'm gonna talk about this talk called Interference Effects and Modified Born Rule in the Presence of Torsion. It's a work done in collaboration with Eduardo Bittencourt from the Federal University of Itajubá and Alexandre Leite Ferreira Jr. from the Federal University of Espírito Santo. There's a previous version of it available on archive on this under this code. However, it's already accepted in PRD. So in the next few days, we shall be publishing an updated version on this archive as well. But nevertheless, the results are quite similar to the ones that are already in this first version of the paper. So I'd like just to make a disclaimer a bit, because this talk is not exactly related to gravity, but is related to quantum mechanics and its relation to non-Riemannian geometry, which by itself is a topic that is very close to the heart to the community of modified gravity. So I think some lessons that could be presented here could be useful also in different contexts. That could be related to gravity. For instance, some lessons learned here from condensed matter physics, from crystal lattices, etc. So let's go. So basically, this first part is you are all very well aware of this issue that geometry actually can be divided basically in two parts: differential geometry in a metric and also in the connection. The metric is related to the sizes of, is to measure the sizes of things, of vectors, of tensors, the magnitudes, and the connection is related to the transport, parallel transport of objects in a manifold, in particular in space-time. So in principle, they are independent quantities. However, you can relate them, as you know. For instance, the connection can be divided in three parts. One of them is completely related to the metric, which is given by the Christoffel symbols, and it measures the non-preservation of directions when vectors move on a manifold. You have the non-metricity, which is related to the non-preservation of sizes of vectors when they are transported in a manifold. And also you have the torsion, which is related to the antisymmetric properties, possible properties of these symbols here, the connection symbols, which is related to the non-closure of infinitesimal parallelograms in a manifold. So it's related to these loops, to this non-closure of these loops. So in this talk, I'm gonna explore the issue of torsion I'm not going to explore these other issues of the connection, but I'm going to explore torsion actually. And as you know, as were already presented earlier this morning, torsion appears naturally in gauge theories of gravity, in teleparallel gravity, in f of t, and in many modifications of gravity. And it also appears in systems like in condensed matter. You can, for instance, model some defects by torsion, and then it appears naturally from the introduction of these defects in some material. Not only torsion, but also no metricity. But in this case, I'm going to talk exclusively about torsion. But it is mainly explored within relativistic quantum mechanics or quantum field theory or general relativity or modified gravity in general. But it is not much explored in non-relativistic quantum mechanics. And the reason is that has always been treated torsion as giving rise to a non-unitary time evolution in non-relativistic quantum mechanics. But in this talk, I'm going to explore a bit further this issue and see if there are some specific kinds of torsion that could be modeled by some materia that we could circumvent these difficulties of the non-unitarity. We can redefine some rules and derive some, in principle, measurable effect due to the presence of torsion. So basically, the way that we introduce connection and torsion and these quantities here in this talk is based on the view binds, which basically map these coordinates x into these x primes. And they define a local Minkowskian metric. And then using this language, you can define the connection this way, using just the derivative of the view bind defined here. And then you see the connection that is derived from the view bind. And we are assuming here, we'll be assuming a metric connection. So the torsion can be found, is found from the anti-symmetry of the connection. And it is given by this quantity here, basically the curl of the view bind. And also the curvature tensor is given by this quantity here, this non-commutator of this derivative. Okay, so we are going to use this language and we are going to see what we find from this kind of language and the kind of transformation that is common in condensed matter physics and what kind of geometrical structure we find. So these are the basic quantities. We are going to, as I already said, analyze non-relativistic quantum mechanics. So we are going to introduce geometrical degrees of freedom by a non-minimal coupling with the wave function through here the connection. Here you have the Laplacian, so you will be working on a three-dimensional curved, in the sense of the connection space. So we can, or at least with connection coefficients, not necessarily curved, but in non-Cartesian coordinates. But in general, we write the Schrödinger equation in general in this form, which, if the connection has torsion, then it can be replaced to this form here, where T is the torsion tensor. So you see here the presence of the torsion that brings a contribution that is proportional to the derivative of the wave function. So it is not a potential like this, that is just a function multiplied by the wave function, but you have the derivative. And this is the origin of problems, usual problems in non-relativistic quantum mechanics. So, I mean, this is a general way of introducing time as well, but we won't be dealing with this. So now I'm going to show you how torsion, in fact, will be introduced by that kind of transformation that I just mentioned. The trick that is usually used in condensed matter physics is you have a technique that you can remove. So you imagine that you have a crystal lattice that could be 3D or in this case 2D. So you have this crystal lattice And then you have each individual element of the lattice here that they are separated by a tiny distance. And what you can do is to remove these points here in this line from 0 to a very long value of x1, and then glue together these other remaining parts to have something like this. And then this removal and transformation in the grid of this lattice that I can use to describe the coordinates of this lattice is gonna bring an effective torsion. So this kind of procedure here is described. I mean, this image is taken from this Kleinert book, Kleinert paper actually, which is was basically for us the main source of motivation for this paper. So that kind of removal can be effectively seen as a transformation in the coordinates of that describe the lattice of this form, where we are transforming these the x2 by using a function here. This phi is a function that is the arctangent function of the coordinate x2 divided by x1, since we are here working in 2 dimensions for simplicity. And here you have the derivative with respect to the other coordinates. And epsilon here measures then basically 2 things. Measures the number of elements removed from the lattice that in 3D could be planes, but in 2D could be just the points of the lattice. And it measures also the distance between the lattice. So we place here much more than 1. Actually, this quantity here will be treated perturbatively. This is what this language means, that this correction will be treated perturbatively in our approach. So, I mean, in order for this to be able to work, you need to have very close elements of this grid. So the issue is that if we induce a transformation using this function, it will naturally induce a torsion, because you can see, for instance, you can see that this is a multi-valued function. So usually in differential geometry, you only work with single-valued functions and C infinity, C2, etc. functions that are all well-behaved. But here, we're going to go to a non-holonomic basis in which it's produced by this multi-valued function that basically the partial derivatives of it do not commute because it's multi-valued. And you can see that by calculating an integral of a surface that is enclosed by a loop. And then you see that this commutation of the second partial derivatives is not 0, but is given by this 2 pi. And this is basically the source of the torsion, because you can see from that transformation here, this transformation induces, can be seen here, an E. From this E here, induced by this transformation, we can calculate the connection this way, coefficients, and obviously the torsion coefficients as well. And then you see that the torsion involves this commutator of the derivatives of the function phi. So if the function is multi-valued, any function that obeys that kind of kind of non-null holonomy or a loop, let's say it will give a torsion like this. So as this quantity here gave 2 pi, obviously this commutator, it's a Dirac delta function centered at the origin. So we have here naturally a torsion induced in this lattice that is proportional to this tiny parameter, tiny dimensionful parameter, and also the Dirac delta function. epsilon here, this other epsilon is the antisymmetric symbol. So basically, this induces from the non-minimal coupling that we can do this way. This induces a correction in the Schrödinger equation that we can move, not retain much in the details, because you also induce a metric, etc. So you need to be aware of that. But in the end, you find a Schrödinger equation that is modified this way. So you have the free Schrödinger equation, because I don't have any potential, actually, plus a geometric term that is given by the Dirac delta function like torsion. And here's the proportionality with the derivative of psi. So usually this can be done using the techniques presented in Kleinert's paper that I just mentioned from the early 2000s. But in this paper, we went from here to the last consequences, because people usually stop here and look, this is non-unitary, torsion in general is non-unitary, leads to a non-unitary evolution, etc. in non-relativistic quantum mechanics. But here we want to explore to full extent this issue. So in the paper, the first thing is to solve this wave function here and try to see if in a loop, that is where torsion appears. Remember the parallelogram, when we imagine a loop, any modification can appear due to the torsion effect. So we divide the wave function in two pieces. The first one is the free wave function, and you have a correction here that is governed, controlled by this parameter epsilon. So we find the Schrödinger equation for psi1 for the correction. To control this psi1, we solve this equation actually by looking at the very nature of the discontinuity. So we use the Schrödinger equation and we integrate the Schrödinger equation around a very small square that encircles the origin. And we analyze what happens if this square goes to 0. And then we find that, indeed, due to the Dirac delta function, it does not go to 0, the left-hand side. So you have a contribution on the right-hand side. And it is the contribution that gives this jump to the wave function. And this is the central equation to all the analysis, basically, to finding psi1. So, to give an example, the first very simple example is the case of a plane wave solution, in which we imagine that we place here a plate centered at x1 equals 0. So you have a double slit experiment, one slit on the left and right, and we prepare the wave function very far from the origin. So we pass the wave function through the slits, and then we want to see what is what would be the interference pattern if we could interpret that the amplitude of the wave function as a probability or as an interference pattern. I'm not entering much into the details. I'm assuming that this is the case. So let's just try to see the interference pattern at a screen on the right of the double slit. So basically, since we set the modification just on one branch of the wave function, for instance, the left, the right is given by the standard wave function, and then we analyze the discontinuity in the left, which using this equation here, we pick one of these cases, then we integrate and differentiate, and then we find that there is a discontinuity governed by a function of the modes of the plane wave. So we find a correction for this new wave function after it passes the defect, and is given by a quantity like this. Whereas modified, it's also a plane wave, but it's dephased by this theta that depends on epsilon, and also depends on the modes of the wave. So we basically calculate the probability, let's say the interference pattern, so what would be the probability density when these waves interfere. And then we find a modification with respect to what would be expected, governed by this theta here. So you have a dephased interference pattern, much similar to what is found in Aharonov-Bohm effect, where you have a flux of a magnetic field, and then the waves are propagated around this flux, and then in the end they get dephased due to the presence of if you have the flux or not, then the particles, the interference can get, the interference pattern can get dephased. This is exactly the case. If you have the torsion, the pattern would be 1. If you turn the torsion on by removing these layers, you would have a difference. But to go to a more realistic scenario, we assume a wave packet solution. So we integrate the wave packet in many modes, which in the end gives this kind of expression where A is the width of the wave packet, psi is this parameter that depends on time, and then you have here some parameters that depend on the point in which the wave was prepared to the point in which the wave is right now. So this is the let's say the free wave packet without the torsion. And the correction we find from that condition on the center of the plate due to the torsion, where we find a correction that, I mean, the details can be seen in the appendix of the paper that it's available on arXiv, but we go to Bessel functions, then we separate in an infinite series, then we work on that and simplify. In the end, we find a correction to this psi1. So let's move to this interesting part in which the waves are interfered. So if I interfere them, the left and right, we produce what would be the standard case plus a correction here. So actually, we predict, let's say, a correction in the interference pattern of this double slit experiment due to the presence of torsion. So for this graph here, we used parameters of the order of nanometers. So the slits are separated by 10 nanometers. The apertures of the slits are 0.1 nanometers. The modes of the function are of the order nanometers to -1, and also the plate is located some nanometers after the location of the slits, and the width of the wave packet is also some 0.1 nanometers. So we find this shift where this difference in the maximum of the fringe, the interference fringe, is of the order of 10 to -2 nanometers, so 0.1 angstroms. We also suppose that the parameter here is of the order of angstroms, 5 angstroms. So we find something like 0.1 angstroms in this difference here. Well, it's small, but we verified that many double slit experiments and also a Aharonov-Bohm type of experiments are being performed using carbon nanotubes and quantum dots that are prepared with this order of magnitude of spatial quantities of the order of nanometers, a few angstroms. So we expect that this is not so we expect. So I mean, we didn't contact yet any experimentalist actually involved in this, but we expect that this wouldn't be so far from being detected if possible. But this depends, this interpretation of the psi squared depends on the validity of the Born rule, right? That the information that you can derive from the wave function is actually the probability density of locating a particle, which depends on the probabilistic interpretation of the wave function. So it depends, for instance, on the unitarity of the evolution. So this sets a problem because I mean, due to the nature of the Schrödinger equation that we found, actually the continuity equation for the psi squared is modified. So it is not satisfied. It is given by, it has a source here. However, this source is due to a term that has a measure zero set, which is due to a Dirac delta function centered in the origin, due to the removal of layers of a line in the lattice. So we expected that somehow we could rearrange this continuity equation and modify the Born rule such that we could still have a probabilistic interpretation for the psi squared. Indeed, this is the case. This is just the wave functions. This is exactly what comes in the correction when we assume the wave packet. So this expression, we can actually redefine the probabilistic, the Born rule. We can modify the Born rule by saying, look, we are going to measure the expectation values of quantities in this approach so that probability cannot be growing, cannot be coming out of nowhere or disappearing. We need to modify the way that the rule that we use to measure the expectation values of quantities. So if we modify this way, then the continuity equation is satisfied for the new, also for the new current density. And we can indeed have like a constant normalized probability density, which if we integrate everywhere over the plate, it would give 1. So if we use this modified Born rule, where P is the usual psi squared. So if we modify this quantity here by this, we can absorb this correction here in the left-hand side. So it's a very simple trick, but that at least allows us to do that. And this can be done if we have this zero measure Dirac delta function like correction. And this modification of the Born rule that we propose also induces a modification in the scalar product in this Hilbert space that could be found from the polarization identity that connects a given norm in a Hilbert space to a scalar product in a Hilbert space you can calculate. So basically, the quantities are going to be defined using the P. So with this approach, we found a way to at least, in this perturbative way, still have a probabilistic interpretation. Obviously, as if the function, where you are calculating expectation values encompasses regions that do not contain the origin, then obviously the new Born equation, let's say the new Born rule, reduces to the previous one. So that's why our probabilistic interpretation of the psi squared on the plate, on the screen that where the particles hit would be valid. So, but in any case, we still explored this case if we want to have a coherent picture. Nevertheless, this is an effective approach that applies to this case. Torsion still has problems at a fundamental level that in this Copenhagen interpretation, maybe just to raise the ball here, something like the Broglie-Bohm approach, where torsion could emerge from this coupling with the functions, with the decomposition of functions of the wave function in the Broglie-Bohm approach, could solve this probabilistic interpretation as well, but we didn't explore this in further details. So just to summarize, we introduced a modification in the non-relativistic quantum mechanics due to torsion, which usually is expected to bring a non-unitary evolution, which indeed it does if the Born rule is kept unchanged. But we can redefine the Born rule in order to take into account this torsion induced by a topological defect that allows to have still a probabilistic interpretation and derive a measurable effect that could be measured in experiments, for instance, involving carbon nanotubes or experiments that are being performed within condensed matter physics. So this is the main point. These are just some references. The Kleinert has been the main paper, but we have also followed all these papers as well. These are the main papers for this paper. So thank you very much, and gracias.
Thank you, Yarli, for the nice talk. Let me see. Is there any question?
There are no questions in the room.
You said there are no questions?
Exactly.
Okay, so if anybody wants to ask, I might comment something. So in my view, the minimal coupling principle is usually not very well defined when you include torsion and non-metricity, and it depends a lot on what kind of fields you are treating with. And the Schrödinger equation more or less is the low energy limit, if you want, of both the Dirac and the Klein-Gordon equation. But in my view, the Klein-Gordon field does not couple minimally to the torsion, while the Dirac field might couple to it. So in order not to commit to this kind of recipe, it might be interesting as well to include other kinds of couplings to the torsion from the Schrödinger equation, like kind of doing an effective field theory approach, and then see if the different terms give you like different kind of effects, or they spoil unitarity in different ways, or maybe they can cancel the contributions or stuff like that. Have you thought about this?
No, I haven't, but I mean, that's very interesting because let's say that this kind of, so let's suppose this kind of effect is indeed measurable. So this way you could distinguish between different couplings between geometry and quantum mechanics and matter. So this could be a way to distinguish between these different recipes for couplings.
Mm-hmm. Okay, thanks. So any other comment or question? If not, maybe let's thank Yarli again. Thank you very much for the talk.
Thank
and
you.
Let me introduce the next speaker, who is Albert Petrov from Universidad Federal de Paraíba. And he's talking to us about this gravitational topological term in Einstein-Cartan group. So, Albert, yeah, you're there.
Well,
What are they?
hello to all. Can you see my screen?
I can see you, but not your screen yet. Let me see.
Now.
I already give him the
Presentator right.
Permit here.
Yeah. So I think it should be below the screen.
And now.
Oh yeah, I think it's sorry. Yes, now I can see it.
Well, first of all, I am grateful for organizing committee for possibility to participate in this conference. And what I am going to present now, our paper with this title, Induced Gravitational Topological Term and Einstein-Cartan Modified Theory. This is number of preprint. And this paper is our first attempt to enter to studies of torsion of non-Riemannian geometry, non-Riemannian gravity, and moreover, actually it is some intersection of non-Riemannian geometry, quantum gravity second, because we will calculate some quantum corrections. Some exact solutions third. And I already said that we will with non-Riemannian geometry, and we will show perhaps one of the times how we calculate quantum corrections in this theory. First of all, why non-Riemannian geometry? It is known that many studies of gravity performed within usual Riemannian geometry. However, within our results are accelerated expansion of the universe, gravitational waves, observation of black holes. It is clear that it is reasonable to test various possible models of gravity. That is, we consider not only general relativity, moreover, that the general relativity is a problematic theory in the sense because general relativity itself is first non-realizable. Second, it does not allow for an explanation of accelerated expansion of the universe. So we should do some extension of gravity, of usual Einstein gravity. Moreover, I want to say that already in years 80s, there was published a book by Russers, Ponomarev, Barvinsky, and Obukhov. They classified various approaches in gravity in dependence on three fundamental properties introduced within these approaches. That is curvature, torsion, tonicity. They claim that there are 8 various models. So in this talk, we discuss Einstein-Cartan gravity, gravity in which we have both curvature and torsion. In this case, well, torsion is non-dynamical, but non-dynamical, therefore, it can propagate. In principle, we can consider also that torsion propagates, but it is another step. And why also interesting, I didn't mention it already, because there is some bridge in these studies and studies of Lorentz symmetry. Therefore, in this case, we can have some kind of non-Riemannian geometry with torsion, because now we consider some generalization of four-dimensional gravitational Chern-Simons term. We know that four-dimensional gravitational Chern-Simons term, in certain sense, in cases, describes the Lorentz symmetry breaking, can be with use of the Lorentz symmetry breaking. In this case, we show that the Lorentz breaking vector is related with the torsion. And one more comment. Here we use topological invariants. Topological invariant is known that very important line of studies. We know that curvature, scalar curvature is topological invariant. In all the dimensions, higher dimensions, we have Pontryagin term, R, dual R, square of, in certain sense, square of Riemann curvature, proportional of Riemann curvature. Then we have Gauss-Bonnet. In principle, in topological invariants, we can construct level of gravities. Level of gravities which can be applied for higher dimensions. So now we deal with topological invariants, but in this case, we introduce torsion. What we are going to this is what we are going to do now. First of all, how we introduce the torsion within our theory. As I already said, one of our principal aims is to calculate one loop corrections. One loop correction. Why it is essential? It is known, there is a well-known methodology in quantum field theory, especially within Lorentz breaking context, that new terms can be generated at the one loop level as quantum corrections in a theory in which the corresponding field, that is, in our case, gravitational field, expressed in terms of metric or torsion, and in this case we will have both metric connection and torsion, is coupled to some fermions. Then we integrate over the fermions and obtain, therefore, the one loop effective action of the fermions on the gravitational background. This is the manner which was applied to obtain various terms. There were some papers in which the four-dimensional gravitational Chern-Simons term was obtained just through integration over fermions. There were, of course, a lot of studies where various new terms in electromagnetic sectors were obtained through integration over fermions. Carroll-Field-Jatif term, ether term, higher derivative terms. And in all cases, the methodology is the same. We consider the action in which we couple fermions to our field, whose effective action we want to obtain, integrate over fermions, obtain functional determinant, that is one loop correction, and we obtain the new theory with an additional term which arises namely as a quantum correction. I already mentioned that this is the manner which allowed us to generate the Carroll-Field-Jatif term and the four-dimensional gravitational Chern-Simons term. We start with the following action of fermions in a space-time, curved space-time, that is Riemann-Cartan background. As usual, here we have integral over 4 dimensions. We have tetrad, whereby we have connection within Riemann-Cartan methodology. Connection is independent of the metric and therefore of the Wilbein. And the torsion can be obtained on the base of the correction. Here we assume that our theory is massive. And we can, in principle, deal with tetrad formalism. That is, we introduce two types of bases. Covariant basis, Wilbeins, and or contravariant, theta. Covariant or contravariant. We can, as usual, relate metric with the Wilbein. We can introduce curved Dirac matrices, covariant derivatives constructed on the base of our connection. This is our connection, spin connection. Spin connection, so it is defined in terms of sigma Dirac matrices. This spin connection is necessary every time where we couple our spinor field with gravity. We can make some things. We can require that in symmetric it is constant, covariant derivative is 0. We introduce torsion to form as a covariant derivative of our one form, and we can introduce, as usual, the two form of curve, as usual. Omega here is connection. We can explicitly write our torsion in terms of the tetrad Wilbein and connection. Torsion. It is antisymmetric as usual with respect to indices. And if we deal with connection, connection is an important ingredient. We know that in usual Riemannian geometry, connection is not zero. Therefore, we can split our general connection into some parts. This omega bar is torsion section, Cartan connection, torsionless, therefore the corresponding torsion is zero. And K is so-called contortion tensor. Tensor which is expressed in terms of the torsion. This is the expression relating contortion tensor with the torsion. And omega bar, torsionless, is expressed purely in terms of the view binds, and can be related with so-called anolonomy or Ricci rotation coefficients. These Ricci rotation coefficients can be directly related with view bind. This is the expression. As the basic definitions. So, what we are going to calculate quantum corrections. We can play with this action, use some tricks with derivatives. This is our starting point, our initial action. We remind that omega, our connection, omega, which serves to introduce the gamma vector connection, omega is related with omega bar torsionless and contortion. So we can rewrite this expression in terms of torsionless connection and contortion. We proceed calculations. After some transformations, we arrive at the following expression. Now we see that that is similar to the usual action of spinors in a curved ground. Here, nabla is a covariant derivative expressed in terms of Riemannian connection. Here we see that here we have omega bar. Again, omega bar is torsionless correction. Torsionless corrections. Omega bar, it determines gamma. Gamma is contraction of this object with sigma. Sigma matrices here, like here. Contraction with sigma matrix. Equation 5. So, we see that our result is written in terms of torsionless correction, and therefore our action, torsion correction, connection, and covariant derivative constructed the base of the torsionless correction connection. And here we have torsion, dual torsion vector. That is the contraction of the torsion tensor. And let's read a symbol, axial torsion. Vector torsion, axial torsion is this object. So we see that when we write this action of spinors coupled to the gravity, we have the action which is rather to the action used in our previous paper of 2007, the gravitational Chern sign, with only difference that in of the constant vector Bmi, which introduces Lorentz symmetry breaking, here we have axial torsion. This is the first new effect that in principle, perhaps it can have a mechanism how we can generate the Lorentz symmetry breaking. If we assume that the expected value of torsion is small, but not zero, of axial torsion to the center of this vector, this torsion can be responsible for introducing the Lorentz symmetry breaking in our curve space. So this axial term plays the role of the Lorentz vector. So for this quantity of spinors, what can we do? We can calculate as well the fermionic determinant, the trace of logarithm of this operator. The trace of logarithm of this operator. This is the expression for the one loop effective action, which we are going to see. How we can calculate? We can apply all methodology we used when we calculated the gravitational Chern-Simons term for dimensions 2007. How we proceed? First, usually if we deal with the proper time method, we should consider quadratic operator. Quadratic means that quadratic in space-time derivative. That is, it should involve second space-time derivatives. So we need to complete this operator to the quadratic operator. How we proceed? We add the following operator. We add the following operator. The following determinant. We add the following determinant. Trace of logarithm of this operator, it does not involve usual connection, but it involves dual torsion vector. We add this determinant and this determinant, this trace of logarithm. This trace of logarithm, here the sign of logarithm is omitted. This trace cannot generate the cross term which involves both metric and torsion. It will generate only the purely torsional terms, that S square, ds square, higher orders in torsion, but everywhere pure torsion. At the same time, we are going to consider cross term, that is term which depends not only on torsion, but also on metric or on the Wilbein. So this term will not affect the desired cross term. Cross term is the term which involves both metric and Wilbein. We sum this trace of logarithm and this trace of logarithm. We make some simplification. So we obtain the desired quadratic operator, calculate the contributions of second order in corrections with one derivative and first order in axial torsion. This is the result. And third order in connection and zero order in derivatives. So as a result, we proceed along the same lines as with the Chern-Simons term, gravitational Chern-Simons term. As a result, we arrive at the following new term. This is the desired Ni-Yang term, which involves both torsion and usual Cartan connection. Usual Cartan connection, torsionless connection. So this is new term. It can be expressed in terms of the differential forms. We can say that in this case, we can write our term as a product of two topological currents because epsilon times this term is a topological current corresponding to the Chern-Simons term, Chern-Simons topological current. So we can write our action as a product of two topological currents. This is the Chern-Simons topological current and the axial torsion, which is treated as also as a current, Ni-Yang current. What we are going to do now? Here we write the gravity action which involves usual usual gravity action plus the Nian term. In usual notation, this action can be rewritten in this form. So let us consider this action. It involves both curvature part and torsion part. Torsion is here. Torsion multiplied by the Chern-Simons current. Let us obtain the equations of motion and let us solve these equations of motion. We rewrite our connection. Here, gamma is the full connection. Gamma is the full connection. That is, it involves both Levi-Civita connection, usual one, and contortion. Levi-Civita is a connection which is present in the zero torsion case, and K contortion is responsible for the torsion case. We obtain the equations of motion, varying our action with respect to the metric. This is our Einstein-like equation, but with new source, which is x, corresponding to variation of this term. So it essentially depends on the torsion, and this equation is obtained through variation with respect to the contortion. Two equations let us solve. Let us imagine that we have no matter, only gravity at torsion, that is only metric and torsion. There is no matter, there is vacuum. Usual matter, that is fluid, etc. We calculate the trace, obtain the following expression for torsion in terms of our Nian vector, our topological current. And so we see that our equation of motion implies Chern-Simons topological current is related with this C current for the Chern-Simons current. Therefore, we see that Chern-Simons topological current is actually nothing more than a source for the torsion. We can eliminate S with use of this expression, eliminate S topological current for the torsion, and from our action on shell. And as a result, we stay with the following on-shell action, which involves general relativity using Einstein-Hilbert term and new term that is square of the Chern-Simons current. And we can verify in principle that, for example, static spherically symmetric metric will solve this equation, because when we obtain the modified Einstein equation, C, our current, Chern-Simons current, will disappear for spherically symmetric metric. It is known result that Chern-Simons gravitational term and Chern-Simons current disappear for spherically symmetric metrics. So for spherically symmetric metrics, in particular, Schwarzschild, Reissner, Nordstrom, all these metrics solve the modified equations of motion. Kerr metric, no. Kerr metric breaks rotational symmetry. While the Cotton tensor is not zero, Chern-Simons current is not zero, so for the Kerr metric, the situation is much more delicate. So, what we actually did, let us quote, effectively we formulated a new theory involving both metric and torsion. Second, we obtain new term, new topological term, Nian term, as a quantum correction. and we showed that this term is finite. Third, we proposed a new mechanism for Lorentz symmetry breaking. So, in principle, we can deal with more studies, verify consistencies of more metrics. Thank you for your attention.
Thank you very much, Albert. Let's see if there is anybody with questions in the audience.
There are no questions.
I have a question.
Okay, go ahead.
Hi, Albert. It's Yarley.
Yeah, I am happy to see you here.
Yeah, me too, Albert. I'd like to know if the so you introduced the Lorentz violating term.
In principle, better to say that it is a consequence that is under certain conditions, our new term can be treated as a Lorentz breaking term. But in principle, the torsion is an independent field, so we can consider situation where the expectation value of torsion is a non-zero constant vector. So in this case, we will have Lorentz symmetry breaking. But by definition, this term is not yet Lorentz invariant. It will be Lorentz invariant if Lorentz breaking. It will be Lorentz breaking if we assume that our torsion has non-zero expectation value.
I see. But you don't have yet any expectations for the dispersion relation of those fermions coupled portion, right? Or do you have?
Dispersion relations for fermions. I think dispersion relations for fermions in this theory should be the same as in usual theory. Moreover, in most part of studies, if we deal with Lorentz symmetry breaking, we consider dispersion relation on the flat background. Dispersion relation on the curved background, sincerely, we didn't study yet. In principle, I think it can be further study.
I see. Okay.
Thanks, Yarley, for the question. Any other questions or comments? Okay, so if not, let's thank for the presentation. And let me introduce the bit of the session. Theodore Lavov at UCM Madrid. It sounds the name sounds weird in English. It's Universidad Complutense de Madrid. He's going to talk about future rip-like events in cosmology.
Hello there.
So, okay.
Do you hear me?
Yes, I can hear you. Can you share your screen and so on?
Yes, I'm trying to. Okay, now I can.
Yes, I think that now you have the.
Yes, now I have the rights to see.
Okay.
Yeah.
Okay.
Okay, so go ahead.
It sounds a bit weird, the University Complutense de Madrid in English.
Yeah, or Complutense University is just weird.
Yes. Well, in any case, first of all, thank you for having me here today. And so the main goals I want to explain here. I will try to introduce some dark energy models that could, in principle, be compatible with our current universe and can drive the expansion of the universe towards some different future fates than those predicted from the Lambda CDM model. And more specifically, I will talk in this presentation about two different dark energy models that are basically we have studied in two different works. The works with Mariam Mohammadi Lopez and Prado Martin Moruno, which are my PhD supervisors. So this little talk will be based on these two works down here, basically, The first of them is already available online, and the second is currently under production, so we hope to be available soon. In any case, to start with, I would like to comment that according to the current interpretation of the observational data within the general relativity framework, today we know that the density, the composition of our universe is roughly 1/3 of matter, either with both ordinary and dark matter, and the rest of the composition of the universe is due to some exotic energy content with a negative pressure that pushes the cosmos further into expansion. And that component is called ordinary dark energy. So today we have these funny pie charts here that basically tell us that the composition nowadays of the universe is more than 90% of the composition falls into the so-called dark sector. In any case, today we know that we are currently under a dark energy dominated area, and if that dark energy component continues to behave as we expect it in the future, it will be even more dominant in the future, which is fairly interesting to investigate in these dark energy models. However, even though this is the dominant continent right now, the very nature of this dark component is still unknown today. On the other hand, I also would like to point out that even though the Lambda CDM is the best model, the model that offers the best fit overall to the cosmological observation, it does have some unsolved problems. Here I list just to make a point 3 of them. The first, the cosmological constant problem, that stands for the cosmological constant from the Lambda CDM model, differs in several orders of magnitude with the value expected from quantum theories. Another very famous problem is the nature of the dark sector and the nature of the dark energy, which is still enough, and the nature of the dark matter, which we have some candidates nowadays, and I also think we already had some nice talks about that, but we don't have any confirmation yet. Also, another very interesting problem of this model is that in the recent years, it has some tension in the cosmological model has been built up. And the most famous of that cosmological tension is the Hubble tension, which in a nutshell stands that for local measurements of the Hubble parameters tends to reflect higher values of H0 when compared with more distant measurements like the Planck collaboration. So having all this in mind, one may think about the Lambda CDM model, even though, as I said, is the most complete, in some sense, model we have nowadays. One may think about this model as just some useful theory, effective theory. And this opens the door to a wide alternative, to a very great number of alternatives in order to describe the late time acceleration of our universe. And basically all these theories can be packaged into 2 groups. On the one hand, we may have some proposals which modify just the dark energy content of the Lambda CDM model. And on the other hand, we have other proposals that choose to modify the underlying theory of gravity instead. In the latter case, it's interesting to note that one can achieve some expanding cosmologies that matches the observation, not with in the inclusion of some exotic matter content, but with the modification of the underlying gravity by itself, which is fairly interesting. In any case, in this talk, I will focus on the first approach. That is, I will keep general relativity as the correct theory of gravity, and I just will introduce you 2 different models for dark energy, which of course differs from the cosmological constant and have some different future fates. But before going to these specific models, I also want to address that whatever the origin of this dark energy may be, it can be effectively studied through its equation of state parameter. That is the ratio between the pressure and the dark energy density, or the ratio between the effective pressure and the effective energy density in the case of alternative theories of gravity. And in this picture, it's important to note that the cosmological constant plays a very critical role in the W line. That is, if we have a cosmological constant, we have a W which value exactly -1, which tells us that the dark energy density remains constant throughout the expansion of the universe. However, if this W parameter is even slightly below that this -1 value, the dark energy density begins to grow with the expansion of the universe and eventually pushes the universe into what's called the super-accelerated expansion. And this is precisely what we call phantom dark energy. So this is a really fine-tuning problem, because if you have slightly below -1 in this parameter, you may end up in an entirely different universe from the point of view of future fates. In this, so therefore, the observational constraints are very useful in order to unveil some hints of the very nature of these dark components. And here I brought just some 3 fits, cosmological fits, just to make the point. How are the current data going? The first one is the Planck 18 released. Then I also write down here, this is the Abbott et al., which is from a dark energy survey, and the last one is from the Pantheon sample. And as we can directly see, all these 3 values are in principle compatible with having a dark energy with phantom nature. Well, of course, there are a lot of more data samples out there. Some of the data sets are more prone to having a dark energy with phantom behavior, others are less intolerant to that idea. But the point to make here is that today having a phantom dark energy is not observationally excluded at all. And this is fairly interesting, because if we have phantom dark energy, the behavior of our universe will be very different in the future from that of the lambda CDM model. And precisely this phantom dark energy may introduce in the future expansion of our universe some cosmological singularities, which are very interesting to study. And some of these cosmological singularities that I will refer on are these ones. Maybe the most famous is the big rip singularity, in which the size of the observable universe, along with the Hubble parameter and its cosmic time derivative, blow up in a finite time into the future, destroying every bound structure in the universe and ultimately the space-time itself. But maybe less common, less known, there are also different other cosmological singularities intrinsic to phantom models. For example, the little rip singularity can be understood as a big rip singularity that has been infinitely delayed in time, since the only difference is the time of occurrence of the rip, even though in this model the bounded structures are also destroyed in a finite time from present. The little sibling of the big rip is another cosmic event in which the size of the universe diverges with the Hubble parameter, but the time derivative of the Hubble parameter remains constant. And all these 3 events, as I said, they are very intrinsic to phantom dark energy. And as a matter of nomenclature, the big rip is a strong singularity, strong curvature singularities, and the other 2, the little rip and the little sibling of the big rip, they are not properly singularities because they occur in an infinite time to the future, so they are called abrupt events. But in each of these future singularities or events, the bounded structure are destroyed in a finite time to the future. And just here, for the sake of completeness, I have also included in this table the pseudo rip, but this is not a proper singularity since the curvature scalar does not diverge in this event. In any case, these are the possible features of a phantom dark energy model. So now moving to some specific phantom dark energy models, the first model I would like to talk about is given by this equation of state for the dark energy. Here we have in this equation of states, the first part corresponds to a cosmological constant, and then we have some polynomial contribution like pushing further into the negative pressure. For regardless of the value of this exponent alpha here, if the constant A is positive, this behaves like a phantom dark field. And this also can be seen from the equation of state parameter for this equation of state, which is a stroke law can be easily obtained. And we can see here that if A is positive, this equation of state parameter is always below -1. And therefore, the dark energy in this model have a phantom behavior. Also worthy to note that even though in this kind of models, in general, the equation of state parameter can approach asymptotically the cosmological constant value as the scale factor diverge, the behavior of the universe for these models is far different from that of a de Sitter universe, since the dark energy and pressure here are not constant, but they diverge. So this equation has a very wide phenomenology depending on the values of this parameter. And this was studied back in the 2005, and we have recently made also some little contributions here, added some little pieces of information to this table. But basically what we have is that if the parameter alpha is greater than 1, the superacceleration of the universe is even stronger than for the big rip case, and the universe ends up in a singularity at a finite time into the future and for a finite size of the observable universe. And these kind of singularities are also known as big rip singularities or pseudo singularities in other classifications. But for the big rip, for example, here, next one, we have that if alpha goes between 1/2 and 1, we reach a classical big rip singularity. Whereas for alpha between 0 and 1/2, we have a little rip, and the little sibling is for alpha's negative. So this very easy to handle equation of state have all this variety of possible future states of the universe. But now, what about the observational constraints on this model? Well, there have been already works in the literature that constrain these models with cosmological data. Here I bring just to make the point some of these constraints. These are from a past work of Mariam. For the big rip singularity here in this table, I just constrain the alpha equals 1 case, which corresponds to this equation of state, which is nothing but the WCDM model. For the little rip case, in this case, we can choose alpha to be equal 1/2, which corresponds to this equation of state. And as a matter of fact, this was even though the little rip event was already known in other cosmological model, this precise equation of state was the first time this name was given for that event. And lastly, also we have the little sibling of the big rip when alpha is equal to 0. For this equation of state, always also constrained with a cosmological observation. So now here we can see that, of course, the big rip event, as I said, correspond in this case just to having a constant equation of state parameter, which is WCDM model and has been already widely studied in the literature. We have here a fairly compatible constraint with the other I showed you before in the other slides. However, for the abrupt events here, the very little constraints and the very little values for the factor here suggest that even though it's possible to fit this model with the data, nowadays the lambda CDM model keeps being the most preferred model observationally. In any case, either of these three events has been shown to be compatible with cosmological observation, and the point to make here is that our own universe may be described by some of these phantom dark energy model and may in the future evolve towards either of these future events. Now for moving to the second part of the presentation, I would like to discuss some very interesting features of this kind of scalar tensor theories when you have also a interaction with the second derivatives of the scalar field. This, but without introducing new degrees of freedom in the theory. These are indeed a subclass of the more general known Hordensky theories. And in fact, this precise model belongs to the subclass of Hordensky theories that trivially passes the gravitation, the cosmological constraints coming from the detection of gravitational waves. Here we have the two independent functions in this model. The first function k is just a generalization of the Kaysen's model, and the second function g that couples to the D'Alembertian of the field exhibits very interesting features. In fact, it's because this operator here that this kind of model exhibits a mixing between the kinetic term of the scalar field and the kinetic term of the metric. And this mixing between the kinetic terms, this braiding between gravity braiding, is essential in the sense that it cannot be removed through some field redefinition. And this precise term here makes this model very compelling, makes them have very rich phenomenology. For example, for a general background, these models cannot be described with a perfect fluid description. Moreover, it also has been shown that these kind of models can allocate, very easily allocate a future de Sitter asymptotic phase, which is stable in the sense of dynamical systems approach and also in the sense of cosmological perturbation. And most importantly, these dark energy models have also been shown to be able to display some phantom behavior without having gauss or gradient instabilities. However, even though the most common application of these models as precisely to study future de Sitter universes, we have recently found that this is not the most general future fate of these models, since more bizarre futures are also possible. And I will give you in a few slides an example of that. But to be more precise, another also very interesting and cosmological compelling property of these models is the shift symmetric case. That is when the theory, when the model is invariant under constant shifts on the scalar field. This, in practice, implies that the two functions k and g depend only on the kinetic term of the scalar field and not on the scalar field itself. And of course, as every symmetry of the theory, we have a current that is currently conserved. And this here is the expression of the current for the cosmological background. And is this conservation of this current a very interesting feature, because it's precisely this conservation that allows us to infer a lot of properties in this model without the need of writing down explicitly the functions k and g. And to see that, let's just move to some cosmological background. In a homogeneous and isotropic metric, the field equation of this model are those ones. Here, the two first are the equation for the Friedman equation, and the third one is the conservation of the current, which happens to be, of course, the field equation for the scalar field. And because of this symmetry, when the equation of the scalar field is written in terms of this shift current, is almost immediately to obtain a first integral of the system. Thus, it's very easy to solve for the current as some arbitrary constant over the scale factor cube, which means that this shift current will vanish with the expansion of the universe. And that is very helpful in order to characterize the future attractor, as all the future attractor will have this property. The shift current will vanish on them. So now if we want to study which future attractor we can get with this model, first approach will be having a general functions k and g, such as that the velocity of the field is finite. Using this property of the future attractor, these equations of the fields simplify drastically, and we only have remaining these two equations, which is very easy to solve here for h, for the Hubble parameter. And then when the external matter fields are diluted away, this gives a very simple de Sitter attractor, which has been shown to be stable not only in the phase space but also under cosmological perturbation. And also a very interesting property of this de Sitter attractor is that the scalar field exhibits a phantom behavior near the de Sitter attractor. However, this phantom behavior is healthy because there is no ghost, no gradient instabilities around there. However, other kind of future attractors are also possible to be built in these models. And to realize that, very key observation in this is to take a look at the Friedman equation again and realize that if we have such a functions k and g that the velocity of the field grows more fastly than the vanishing of the shift current when the attractor is approached, this contribution here of the scalar field to the total energy can blow up on the future attractor. And if that divergence occurs in a finite time from now, we can get some big Ripon singularities. And this is very easy to obtain some examples. We have recently found some examples of that. For example, this very simple example, when we drop out the chi-sense component and we only keep the braiding term with a power law expression, when considering the external fields to be matter and radiation, we get just these field equations. When it's also interesting to note that the braiding term here has introduced a linear term in the Hubble parameter in the field equations. So now this field equation can be analytically proven, and not solved, but we can analytically prove that when the matter and radiation are diluted by the expansion of the universe, the Hubble parameter and its cosmic time derivative have this kind of expressions, which of course correspond to a big Rip singularity, because in a finite time into the future, both quantities blow up when we consider this set of parameters for beta. So this is a nice example of how one can obtain different fates in these kinetic gravity theories. However, there's still an open question about the stability of this future attractor, and this open question can be addressed under the dynamical system approach. We can write down a closed dynamical system for the system with a usual definition of the variables coming from the Friedman equation. And when that is done, we found out that here we have 6 fixed points in the phase space. And then these are the nomenclature of the fixed points. Here we have the equation of state parameter for the field, the equation of state parameter for the effective fluid, for the total fluid, and in the last column I just show you the linear stability of the model for beta between these two values. So at first glance, this table, it's almost immediately to notice that we have only one repeller in the phase space. And that repeller corresponds to a point that has infinite Hubble parameter, has no radiation, has no matter, and so has no scalar field, has no matter, has only radiation. And in fact, this is just a regular big bang singularity, where the effective fluid behaves like radiation, and the contribution of the scalar field here behaves like negative. It has negative equation of state parameter, but it's not phantom. It's a negative above -1, kind of quintessence. And the other immediate observation in these models is that we have only one attractor, and that attractor has again a Hubble parameter that diverge. But here we have only the contribution of the scalar field, or the scalar field. That is, we have the Hubble parameter diverging with its cosmic time derivative, and we have that the fluid behaves like a phantom, because we get this kind of equation of state parameters for the effective fluid and the scalar field, and both are in the phantom zone for this for these parameters. So this is also a big Rip singularity. Indeed, this is the big Rip singularity that I just told you before. So with this very simple example, with this toy model, we prove that it's possible to have different future events rather than at the asymptotic state in these kinetic gravity braiding theories. And this is very interesting because these theories are very appealing from the cosmological point of view. So that was practically all I want to share today. But just before end, I would like to highlight the main ideas of this presentation. And for the first part of the presentation, the key point is that the Big Rip, Little Rip, and Little Synchronic Big Rip are doomsday predicted by phantom dark energy models that could be described could describe the evolution of our universe because they have already been constrained with cosmological data. And for the second part of the presentation, I would like to highlight that the kinetic gravity braiding theories are very interesting from the cosmological point of view, even though they are mostly used for studying future de Sitter states. We have recently found that they can also be used to model some more bizarre future fates of our universe. And that's all I wanted to present, so thank you for the attention.
Thank you, Theodore, for the talk. Let's see if there is any question in the audience.
There is none.
Yeah, I don't see any question in the chat as well.
Yeah, it seems that all was clear.
Let's hope. So yeah, maybe it's a mixture of that and people being tired already, or maybe they want to have some merienda at this point.
Yeah, probably.
Yeah, I don't have a question myself as well because I'm not an expert in cosmology at this point, but it was a nice talk. So maybe I could be like concluding the meeting. So thank you, Theodore, for the nice talk, and let us resume tomorrow at 10 with a talk by Jean-Louis Rosa. So see you all tomorrow.